Okay, hey everyone. Welcome back. Hopefully you grabbed some lunch and are ready to go. For those of you that are just joining us for this segment, welcome. A few little bits of information. First, we do have a live chat up, so if you have any questions or whatever, please throw them up into live chat. Keep in mind to be respectful. Everyone is sharing this stream, so please be respectful, everyone. Also, if you have any larger questions or you want to post more general questions, you can go to the Piazza page where I have posted a discussion so that you can post them all on there. But yeah, if you notice any typos or whatever, please just throw them up on the chat page. I won't be able to respond right away because I will be busy actually doing the examples, but I certainly can keep an eye on things and try to go from there. Okay, so for those of you that are just joining us, of course, people who saw session 1 have already seen this, but just for those of you that are just getting here for session 2, first of all, I can't possibly cover all the topics in the course. There's 36 lecture hours and there are only 12 review hours, so certainly this does not replace studying. You should go back and study everything. This will probably, for most of you, just be a reminder of some of the things that you maybe forgot to study or forgot that we covered. So after this, hopefully you'll be able to go back and study more stuff. You have over a day and a half to study, so this certainly does not replace studying. The second thing that I want to point out is the best way to study for any of these exams is to just do and understand. Understanding is important. Do as many problems as you possibly can find. Do all the questions in the textbook, all the questions in any other textbooks you can find. Past exams, if you run out of questions on sketching or whatever, you want to do more, Google them. There's lots of resources available. Just do as many questions as possible. That's your best way to study. Third, the problems in these review sections are generally a little bit more challenging than the lecture. So the lecture examples are usually somewhat basic, just to kind of introduce the topics. But now that we've kind of hopefully been doing web work, etc., we should be able to solve more challenging questions. So I hope to be presenting more challenging questions here. If they're a little bit fast for you, that's okay. Just go back and brush up, and these sessions will hopefully be still on YouTube by the time you come back, and then you can catch up after that. There probably will be typos in these notes and typos in the solutions that I do. So please keep in mind that if you think that something is a typo, always best to just go back and check the formula. The formula has been edited by a professional, so they should have no typos in the formula. So when in doubt, check the textbook, and that should be your guide. And last but not least, certainly I can't do a question for every topic that we cover in the review, nor can I go into detail on every topic. So again, this is just meant to brush up on some of the stuff, to maybe go over some of the concepts that are a little bit more difficult that you might want to see again. Just do some practice questions and guide your studying for the rest of the weekend. So let's get started. So this section is all about applications of differentiation. So for example, the first and the big one is well, not the big one, but one of the first ones that you saw are related rate problems. So the idea behind related rate problems are you have some sort of question, maybe you have a volume and a side, or any other physical problem where there's two or more rates rates in the problem. And the idea behind a related rates problem is that you want to be able to find a formula that relates one of the rates that you're given to a rate that you don't know. For example, you might want to know how fast the volume of something is changing, and you're given maybe how fast the length of a side is changing, or how fast the area of something is changing, and you're given that the radius is changing in some way. So the idea behind related rates problems is you want to figure out a connection between the rates that you're given and the rate that you would like to figure out. Usually, almost always, you're not given a formula that relates these rates. Most often, you're given a formula, for example, this, that relates to the this is going to be bad. Looks like I have to restart my, this was going to happen sooner or later, restart my PDF viewer, so bear with me. Okay, open the notes, open the examples. Okay, we should be good now. Okay, so as I was saying before, typically speaking, you don't have any you don't have the relationship between the rates, but you are given a function which gives you a relationship between the variables. So for example, in this situation, we know that volume is related to radius in some sort of way. So we're able to then use the relationship between the variables to figure out the relationships between the rates. And the way we do this is, step 2 is always to differentiate this expression with respect to usually time. So that will give us a relationship between the rate of change in this case, the rate of change of the volume, with respect to the rate of change of the radius. And then once you have this relationship between the rates, you evaluate the rates at a desired point in time or whenever they want you to figure out the rates, and that's about all there is to it. So without further ado, let's get to a question. So suppose that a water trough is 10 meters long and has a cross-section in the shape of an isosceles trapezoid. So for those of you that would like to know what an isosceles trapezoid looks like, it pretty much looks like this. Okay, these are supposed to be symmetrical, and it's 30 centimeters wide at the bottom, so 0.3 meters. I'll do everything in meters. It's 80 centimeters wide at the top, so 0.8 wide at the top, and has a height of 0.5 meters, so this is 0.5. If the trough is being filled with water at a rate of 2.2 meters cubed per minute, how fast is the water level rising when the water is 30 centimeters deep? So I'm going to just draw a line across here. This will be the height A. So this will be a height, sorry, not a height A. This will be a height H. So this distance from the bottom is height H. So just up to this line. And then what I can do is I'll draw these two lines here to help us calculate the area. So these distances here, this is A, and this is A. And then, yeah, and then this is 0.3. And we should be able, this will be 0.525, this will be 0.25, because that sums to 0.8. So yeah, so that should be the geometry. So if we're looking for, say, the volume of the water that's sitting at this height, H, so we have some sort of water in here, we can actually figure out the relationship between H and this A variable, and we'll see why that's important in a second. So the volume of this trough, remember this is in 3D, so this trough has a length of 10, and then the formula for the area of an isosceles trapezoid is 1/2 times the first base plus the second base, where this would be, say, base 1 would be the 0.3, so this base, and base 2 would be the width of the top base. So it's not really a base, but these two sides. So for example, the whole area of the whole trapezoid would be this 0.3 would be base 1, and this whole length would be base 2. But for us, when we're considering the water at some level, a level H, what we would like to do, times the height. So that's the area. So if we would like to figure out the formula for the volume when this water is at a certain height H, the volume is 10 because that's the length of the whole trough times 1/2. The first base is 0.3 because that's the first base. And now what we would like to do is figure out what this length is. So this length, base 2, would be 0.3, which is just the middle segment, plus 2a. Okay, so that's the bottom, and this is essentially the top of the trapezoid, assuming that the water is sitting at height H. Okay, so now we need a relationship between H and A, times H. We need a relationship between H and A, so we can do that by noting similar triangles. So for the big trapezoid, the whole trapezoid, what we notice, we can use similar triangles. And by similar triangles, we notice that the total height of this trapezoid is 0.5 divided by the small height. So the two triangles that I'm looking at are this big triangle and this smaller triangle here. Okay, so the height of the total of the big triangle is 0.5 because that's the height of the trough. And then the width of this triangle, the base of this triangle, is 0.25. And by similar triangles, that has to be the relationship between the height of the smaller triangle and the width of the smaller triangle. So if we rearrange this, we figure that 2 is equal to h over a, and so we figure out that 2a is equal to h. Okay, with that in mind, now we can figure out what the volume of the water is for at any given height. It's 5, because 10 times a half is 5, and then this is going to be 0.3 plus 0.3, and 2a is now equal to h. All this is multiplied by h, so this is 1.5. 5 times 0.3 is 1.5 plus 1.5h plus 5h squared. We can simplify this. Sorry, this should be h. We can simplify this now, and this is 3h plus 5h squared. So now we have a relationship between the volume as a function of h. Okay, so they would like to know the thing that we're given. I'll actually put our givens up here. The quantity that we're given, we are given that the trough is being filled with water at a rate of 0.2 meters per minute cubed. So we know that the rate of change of the volume is 0.2 meters cubed per minute. And what we're looking for is the rate of change of the height. This is what we would like to know. Okay, so here's our relationship between volume and height. It's right here. So now what we can do is take the derivative of both sides of this with respect to t. So dv by dt is equal to 3 dh by dt plus 5 times 2 times h by the chain rule dh by dt. Because remember, h is a function of t. Okay, so now that gives us, since we know that the rate of change of the volume is 0.2, we know that the rate of change of the volume is 0.2 meters cubed per minute. We have 3 dh by dt plus 10h dh by dt, which allows us to solve for, or isolate dh by dt. So we have dh by dt is equal to 0.2 divided by 3 plus 10h. Just by isolating dh by dt, by factoring it out, and then dividing both sides by 3 plus 10h, we're able to get what dh by dt is. Okay, so now we would like to know what the rate of change is at a specific height. So the specific height that they gave was, they would like to know how fast the water's level is rising when the water is 30 centimeters deep. So h in that case would be 30 centimeters. So we can plug in h equals 0.3. And so at the end of the day, the rate of change of the height is 0.2 times, sorry, this is a mistake. There should be 3 plus 10h. Should be 3 plus 10 times 0.3, because they would like it at 30 centimeters deep, so h is 0.3. And if we simplify that, we should, hopefully, if everything is correct, end up with 10 thirds meters per minute. Okay, so again, just the general idea behind related rates problems is they'll give you a rate or 2 or 3, but here in this case they gave us one rate, dv by dt. They gave us the rate of change of the volume, and they asked for the rate of change of height. So although we can't figure out a formula that relates these two rates together, what we can do is, because we know some geometry and we know that the volume of an object that looks like this with an isosceles trapezoid, we can get a relationship between the volume and the height. So here's the relationship between the volume and the height, and we can turn that into a relationship between the volume, or the rate of change of the volume, and the rate of change of the height by just differentiating both sides with respect to time. And then once we have finally, here we have the relationship between the rates that they have and the rates that we want. And so we can actually put that together and figure out what the rate of change of the height is. Okay, so let's take a look at another example. Gravel is being pumped, is being dumped by a conveyor belt at a rate of 30 feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? So we have some sand coming down here and it's landing on a cone like this, and we know that the height of the cone is always equal to the diameter. So we know that h, and in this case the height of the cone is always equal to the diameter, so it's always equal to 2r. So we know that r is always equal to h over 2. So no matter what happens with our pile, we know that this is true. Okay, great. So what do they give us? They give us the rate of change in the volume. We know that the volume of the cone is increasing at a rate of 30 cubic feet per minute. Okay, so there's 30 cubic feet of sand being added to this cone every minute, so the volume is increasing at a rate of 30 cubic feet per minute, and they would like to know how fast is the height changing, dH by dt. This is what they would like to know. So somehow we need to get a relationship between these two quantities. As I said, usually you don't have a relationship between these two quantities, but we can figure out what the relationship between the volume, the variables v and h. We can figure out what that relationship is. Namely, for a cone, the volume is equal to 1/3 pi r squared times h. This is the volume of a cone. And okay, so now we have a relationship between v and h, and that's great for us. And then we might want to go start doing some derivatives and figure out what the relationship between the rates are. But the problem here is that we don't have a kind of a relationship between volume and only h. We actually have a volume that depends on radius and h. And before we get started, we need to make sure that this relationship only has one variable in it. Later on in your careers, you'll figure out what to do when you have more than one variable. But for us, we always have formulas that are only functions of one variable. So volume has to be a function of only one variable. The good news for us is they've told us that the radius is always h over 2. So we have 1/3 pi h over 2 squared times h, which means the volume is 1/3 pi h cubed over 4, or at the end of the day, if you clean that up, it's pi h cubed over 12. So this is the relationship between volume and height. However, we don't just want a relationship between volume and height, we want a relationship between their rates. So what we can do is we can take the derivative with respect to t of both sides of this. So we get pi over 12, and then the derivative with respect to t of h cubed, and that is pi over 12 times 3h squared, so the derivative with respect to h times the derivative of h with respect to t, so just the chain rule there. And so this ends up giving us pi over 4h squared dh by dt. Now, they told us that the rate of change of the volume is 30 feet per minute. So we can go ahead and say that because we now know a relationship between the rates, we know that 30 feet per minute is equal to pi over 4h squared times the thing that we're looking for, dh by dt. And they want that specifically at a specific height. They would like to know what the rate of change is when the pile is 10 feet high. So we can plug in h equals 10 into this, and we get pi over 4, we can get 30 equals pi over 4 times 10 squared dh by dt. So this is what we want, and there's a bunch of numbers, so now we can isolate for dh by dt. And at the end of the day, we get 120 pi divided by 100. 120 pi divided by 100. Sorry, 120 divided by pi. 120 divided by 100 pi is dh by dt. I think that should work out fine. Okay, so again, at the end of the day, related rates questions are pretty much all done the same. You might need some clever geometry and memorize some formulas for volumes of cones and that kind of stuff, most of which is all in the front of the textbook if you need a review. But at the end of the day, related rates are all just figuring out a relationship between the rates that are given and the rates that you want. And then this usually means figuring out a relationship between the variables that are given. And then taking a derivative with respect to time, and then at the end of the day plugging in everything that they're looking for. Okay, I think those are all the related rates problems that I had. No, one more. All right, so let's do this one. I think this is maybe similar to class, but maybe not all of you have seen it. A television camera is positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep up with the rocket. Also, the mechanism for focusing the camera has to take into account the increasing distance from the camera to the rising rocket. Let's assume that the rocket rises vertically and the speed is 600 feet per second when it has risen 3,000 feet. First question, how fast is the distance from the television camera to the rocket changing at that moment? And second, what if the television camera is always kept aimed at the rocket, how fast is the angle changing? So let's just draw almost a critical point of all related rates problems is a diagram. And I am not great at diagrams, but I still know that I need to draw them. So we have that this is the distance, d. This is the height of the rocket, h. And this is 4,000 meters. So here's the camera. And here is the launching pad right here. So this is the launching pad. Okay, and this rocket is going straight up. Okay, so how fast is the distance changing from the television camera to the rocket at that moment? Okay, well, the information they give us is that the rocket is rising vertically with a speed of 600 feet per second. So they have given us, and I'm going to write it up here to save some space, that the height of the rocket is changing at 600 feet per second. Okay, so what they would like to know in question A is how fast is the distance changing? And I think instead of D, I am going to use capital D, only because I'm going to use some D's for derivatives. So I would like to know what the rate of change of the distance is. That is what I need to know. So I need some sort of relationship between these two rates. As I've said before, you don't know any relationship between these two rates, so we need to figure out a relationship between the variables d and h, and then we can take their derivatives to calculate the relationship between the rates. So let's get a formula for d. Of course, d squared, the distance squared by Pythagorean theorem, is equal to h squared plus 4,000 squared. And if you would like, you can certainly take the square root of both of these and then work out the derivative, or we can use a little bit of implicit differentiation and we can make our lives simpler. We can take the derivative with respect to time of both sides. This becomes 2d dd by dt by the chain rule. This becomes 2h times dh by dt. And of course the derivative of this number is just 0. Okay, so this is what we need to know, dd by dt. We are given dh by dt, so that's good. And now we just have to kind of plug in the rest of the variables. These twos cancel, so what we end up with is the rate of change of the distance is equal to the height divided by the distance times dh by dt. Now, when they're asking for when the height is 3,000, so this is equal to 3,000 when h is 3,000. The distance is the square root of 3,000 squared plus 4,000 squared times how fast dh by dt, how fast is the height changing with respect to time. So the height is changing with respect to time at 600 feet per second. And so if we calculate all of this stuff, what we end up with is the square root of, so this is 3,000 squared plus 4,000 squared. This ends up being the square root of, so 3,000, let me see, divided by the square root of, well, I can tell you that this ends up being 5,000. 3,000 divided by 5,000, just because I know 3 squared plus 4 squared is equal to 5 squared, and then all the numbers get square rooted, or the zeros get square rooted, so we just end up with this times 600. And so let's cancel out a whole bunch of, this is 3/5 times 600, so what we get is 1,800 over 5. I guess this is in feet per minute. Okay, I think that should be good. If I haven't made too many mistakes. 1,800 divided by 5 feet per minute. And part B, so that was part A. So part B is asking for, if the television camera is always kept aimed at the rocket, how fast is the camera's angle changing? So the angle, I'm going to write in here, is theta. So again, so here we would like to know d theta by dt. This is what we don't know. Okay, so to figure out d theta by dt, what we're going to do is, this is what we need to know. We need a relationship between theta and h. So because this is a nice Pythagorean theorem type right angle triangle, we can just use our trigonometry. So we know that tan theta is equal to h over 4,000, which means that if I take the derivative of both sides with respect to t, d by dt of tan theta is equal to d by dt of h over 4,000, which of course is equal to 1 over 4,000 dh by dt. Okay, the derivative of tan theta with respect to t is secant squared theta, because that's the derivative of tan theta with respect to theta, times the derivative of theta with respect to t. And that's equal to 1 over 4,000 times dh by dt. We can rearrange this to then say that d theta by dt is equal to cosine theta, cosine squared theta divided by 4,000 dh by dt. And now we're kind of left with a situation where what we need to know is when the rocket is 3,000 feet in the air, we need to figure out what theta is, because then we'll plug it in here. Now, the interesting thing is, most people, if you wanted to go find out what theta is by doing some inverse trigonometric stuff, figure out what theta is, and then take that theta, plug it into cos, and do some more work, that's totally fine. That'll totally give you the right answer, provided you do it correctly. However, what I want to point out is we actually don't need theta here, right? In order to get the answer, we need cos squared of theta. So we don't need to figure out what theta is. If we just knew what cos theta was, then we'd be all set. So let's look at our diagram and see if we can figure out what cos theta is. So this is going to be 1 over 4,000. So let's figure out what cos theta is. So if theta is here, cos is 4,000 over d. And we figured out that d was 5,000. So cos theta is 4,000 divided by 5,000, which is just 4 over 5. So cos theta is 4 over 5, which means cos squared theta is just 4 over 5 squared, times dh by dt, which we were given, is 600. So this ends up being 16 divided by 25 times 4,000 is about 100,000 times 600. So these two zeros cancel out with two of these zeros, and we're left with 96 over 1,000. And I'm sure we could probably radians per minute, probably simplify that further, but you get the gist of the idea. So again, at the end of the day, related rates all comes down to finding a relationship between the variables and then taking the derivative with respect to time in order to calculate the relationship between the rates that they give you and the rates that you want. And I think that's about it for related rates. So let's move on to other things. So max and mins, you guys have seen lots of this before in high school. An absolute max and min, if C is some number in the domain. These are just technical details. Everyone knows what a max and a min are, but I just want to go over it quickly. If I have C, it's in some number if it's some number in the domain of a function, then f of C is the absolute maximum of the function if that value, f at C, is always bigger than or equal to f at x for any other x in the domain. So literally the function cannot get bigger if you plug in any other number other than C. That's what it means to be an absolute max. An absolute min on the domain is the same thing, only for minimums. So it's a special number C, so that when you plug it into your function f, that no other x in the entire domain, if you plug it in, will ever give you a value that's smaller than f of C. This is what it means to be an absolute max. Local maxes and mins are a little bit different. They're more localized. So now we're not talking about a maximum or a minimum over the entire domain. Okay, so this absolute max and min has to do with the whole domain, D. A local max or min just has to do with a small little interval around x. So local maximum means that if you have a value C, a point x equals C, such that when you plug it into the function, it's bigger than all of the other values you could get when you plug in x for x in the little interval around C. So notice the difference between these two things. So a local max has to just do with a little area near C. This has to do over the entire domain. Absolute max and mins are the special values of C that make it a max or a min over the whole domain D. Local maxes and mins are just over small little intervals around C. So here's another one, local minimum x equals C if there is some interval, so that you wrap it around C, and that every other x in that interval, you plug it into f, and you'll never find a smaller value than f at C. That means that C was a local minimum. It's much easier to understand what local maxes and mins are when you see what they mean on a graph. So the idea here is you could, for a local min, you can take this point and you can wrap an interval around it so that no matter what other values of x you pick in this interval, you'll never get a function value smaller than you would have got at x equals 4. So in this case, x equals 4 is a local minimum. Same with the local maximum. Okay, we can wrap a little interval around max, or around the max, around x equals 8, so that every other x value in this interval will never give me a function value bigger than what I got when I plugged in x equals 8. That means x equals 8 is a local maximum. Now look at the difference between this one. This is a local min, because again I can wrap this interval around x equals 12, and I can never find any other point in that interval, so that when I plug it into the function I get anything smaller. Not only that, if this is the whole domain, x going from 1 to say 13, on this whole domain I can never find any x value that gives me a smaller value of the function. This also makes this point an absolute min. Okay, but this is not an absolute min, because you can find another point somewhere on the domain, namely this one, where the function value is smaller than this. So it is a local domain. You can wrap it in a little interval that makes it the boss on that interval, but it doesn't make it the overall boss of the whole domain. This is what it means. This is the difference between a local min and max and a global min and max. So, some more definitions. You guys have seen this before. A critical point of a function is some number C that's, first of all, these are kind of the technical details, C has to be in the domain of f. So it doesn't make any sense to say, oh, I have this critical point, its derivative equals 0, or the derivative there doesn't exist. Okay, that's got to be a critical point. Not quite. It can only be a critical point if it's also in the domain of f. It doesn't make any sense to have a critical point that is not in the domain of f. If this critical point, if the derivative is 0 or the derivative does not exist, that also makes it a critical point. So when you're looking for critical points, you want to look out for two things. First, the derivative equals 0. So that'll give you maybe a list of critical points. Also, any place that the derivative where the derivative does not exist, that will also give you some critical points. provided though you keep in mind that some of these ones might not be in the domain of f. So you have to throw out any points that are not in the domain of f. Okay, so these are the two criteria that you're looking for critical points. Why are critical points important? Well, critical points will tell you essentially where all the maxes and mins are, or give you candidates for where the maxes and mins are. So this says this theorem is if f has a local max or a local min at c, then c has to be a critical point of f. Okay, which means if it's a local max, okay, this is a really important kind of idea here. If it's a local max, then c is a critical point. But it doesn't work the other way. If c is a critical point, is it a max or a min? You don't know. Okay, that requires some other checking. So the idea here is, if you would like a list of all the places that locals, maxes, and mins can happen, you go find the critical points. They will give you a list of all the places that it's possible. However, it won't, not all the points on that list will be maxes or mins necessarily. So just because you found some critical points, those aren't all the points where the maxes and mins happen. Those are just a list of candidates. From the list of candidates, you have to actually do some other work to figure out which one of them are actually maxes or mins. This brings us to the closed interval method for finding the absolute max and min of a function on a closed interval. So if you have a continuous function on a closed interval AB, how do you find the absolute max and absolute min of this function? The first thing you do is you find all the critical numbers, all the critical points on that interval. The second thing you do is you calculate what the values are at those critical points. And the third thing that you do is you calculate the values at the endpoints, because if you notice here, the critical numbers will not pick up the endpoints. Right, so you might run off and you calculate all your critical numbers, and that's great for you. But it's possible that on the endpoints don't show up in your list of critical points. So it's possible that the absolute max or min actually might be located at the endpoints, and your critical numbers won't have, your critical points won't have found them. So not only do you have to check the values of the function at the critical points, you also have to check the values of your function at the endpoints. So this will give you a whole list of values, and then at the end of the day what you do is, it's really simple, choose which value is the biggest and which value is the smallest, and that's your absolute max and min. So let's do an example like that. Okay, so find the absolute max and min of this function. All right. So the first thing that I want to do is find critical points. There are two types. There where the derivative does not exist. F prime. Actually, before I do this, let's just, because we're going to need it, let's figure out what f prime is. That's pretty much what we're going to be doing this whole question on. So the derivative of f is 6x squared minus 6x minus 12. Or if I want to do some factoring, that'll make my life easier later. It's x squared minus x minus 2, which is equal to 6, x minus 2, x plus 1. Okay, so that's the derivative. So now, let's start our absolute max and min problem. The first thing we need to know is critical points. And critical points happen in two places. The first place, and the one that most people forget, is where does the derivative not exist? So what points can you not plug into the derivative? Does the derivative have any problems? And the answer is no. I guess we'll write this like this. None. Oops. None. Okay. You can pretty much you can plug in any value of x into this and you'll get some value for the derivative. So there is no places that this derivative does not exist. Okay, there are other functions, specifically when you start getting denominators with x's in them, where you can have some places where the derivative does not exist. But in our case, the derivative exists everywhere, so we won't get any critical points about looking for where it doesn't exist. The other locations for critical points are where the derivative equals 0. So let's figure out when that is. 6x minus 2 x plus 1 is equal to 0, which means that x equals 2 or x equals negative 1. So these are our two critical points, x equals 2 and x equals negative 1. All right, so our second part to our scheme, let's see what it is. Second point, find the values of f at the critical numbers. So now we take our critical numbers and we plug them into our function. So at x equals 2, so let's actually do this right this way. F at 2, because 2 is a critical number. F at 2 is equal to, let's plug it back into our function, 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 1, and that is equal to 2 times 8, so this is 16 minus 12 minus 24 plus 1, and that is equal to 16 minus 12 is 4, minus 24 is negative 20 plus 1. That looks like minus 19. Okay, so that's minus 19. F at the other critical point, negative 1, is equal to 2 times negative 1 cubed minus 3 times negative 1 squared minus 12 times negative 1 plus 1. Oops. Plus 12 times negative 1 plus 1. And this is equal to 2 times that, this is negative 2, minus 3, plus 12, plus 1. That's negative 5, plus 12 is positive 7, plus 1 is positive 8. So f at negative 1 is 8. All right, now they do give us endpoints. For our interval here, they give us that x equals negative 2 and x equals 3. So step 3 is calculate the functions at the endpoints. So these are the functions at the endpoints. F at negative 2 is equal to 2 times negative 2 cubed minus 3 times negative 2 squared minus 12 times negative 2 plus 1. And that is equal to 2 times negative 8. So I'm going to do, oops. I'm just going to do, that's equal to negative 16. Negative 2 squared is 4, minus 3 is negative 12. This is plus 24, plus 1. And so if you add all that up, you get negative 16 is negative 28, plus 24 is negative 4, plus 1 is negative 3. And finally, the other endpoint that they give us is x equals 3. So let's plug that in. F at 3 is 2, 3 cubed, minus 3 times 3 squared, minus 12 times 3 plus 1. And that is equal to 18 minus 3 times 18, which is 3 times 18 is negative 54, or is 54. That's minus 54. Sorry. 3 times 9 is 27. So minus 27 minus 36 plus 1. And that is equal to 18 minus, this is negative 9, minus 45 plus 1. Sorry, this is negative 9 minus 36 is negative 45 plus 1 is negative 44. I feel like I've made a mistake somewhere. Perhaps not. It looks good to everyone else. So that means f negative 44. Yeah, something doesn't quite make sense to me here. Ah, this is it. Sorry, this is not 18. This is 3 times, this is 54. That's what it was. 54 minus 27 is 27. Minus 36 is negative 9 plus 1. This should be negative 8. Okay. So that should be it. So now we just compare. So of our 4 values, where is the smallest? We have negative 19 here. That's one value. We have 8. We have negative 3. That's another value. And we have negative 8. So the min, the smallest of those, is negative 19. And that happens at x equals 2. And the max, so go down here, is 8. And that happens at x equals negative 1. Okay, so again, this is just a general procedure for finding the absolute max and min of a function. Most likely, you might not see a question that just asks for the absolute max and min of a function. That might not be the question they give you. But what I want to point out at this stage is when you solve optimization problems, this is all you're doing. The optimization problem has 2 steps. The first step is set up the function that you're trying to optimize. And once you have the function set up, then you just do an absolute max and min problem. That's it. So really, optimization is no more tricky in some sense than doing an absolute max and min problem. The only thing about optimization is it's up to you to figure out what the function is. And a lot of times that's the really tricky part about optimization problems. Okay. So I just want to point that out, that essentially optimization problems are just absolute max and min problems done where you supply the function. Okay, so let's move on. So intervals of increase and decrease. So there is an honest-to-goodness definition for what it means to be increasing and decreasing, what a function is increasing and decreasing. But because now we are equipped with all our fancy calculus knowledge, we can then say that if I know that the derivative of my function everywhere on an interval, so no matter what x I have on some interval, if no matter what x I plug into the derivative, if it's always bigger than 0, everywhere on that interval, the function is increasing. If, on the other hand, I know everywhere on that interval, when I plug in any x in that interval, the derivative is always negative, then I know that the function is decreasing on that interval. This is stuff that you guys know from high school. So derivative is positive on the interval, means it's increasing on the interval. Derivative is negative on the interval, means it's decreasing. Your function is decreasing on that interval. Another test is the so-called first derivative test. If I have a continuous function on an interval and it only contains one critical point. Okay, so the idea is I have an interval, only one critical point. If f prime changes to positive, from positive to negative, so the derivative changes from positive, so like this, to negative, like that, at c, so if it goes from positive to negative, so here's c. If it goes from derivative is positive, derivative is negative, at c, then this must mean that c was a local max. Because essentially what it means is it was increasing, 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 derivative was positive to a point, then the derivative started going negative, which means right at that point, it must have been a maximum. On the other hand, if you have a function that changes from negative to positive, so here it is going negative, and here's c, this is the value c, and then it starts going positive again, that means that this is a min. This is the max. So this is the first derivative test. The idea is look at the derivative on both sides of the critical point. If it changes from positive to negative, that must have mean it was a max. If it changes from negative to positive, that must mean that the critical point was a min. It is possible that at a critical point you have something like this, where you have an increasing function, there's your c, and then it keeps going. So it goes from increasing, f prime is positive, to increasing, f prime is positive. In which case this is not a critical, or this is not a local max or min, because the derivative did not change sign. So your maxes and mins happen when the derivative changes sign. The first derivative changes sign. Okay? Concavity. So this is the stuff, it's the same kind of idea, only with second derivatives. So the idea behind concavity is if the second derivative of a function is positive everywhere on an interval, that means the function is concave up. So it looks like a bowl. Concave up looks like this. Oops. Concave up looks like this. Concave up looks like a bowl. Concave down looks like this. Concave down. Okay, so if you have a situation where the second derivative is positive, so this would be the second derivative is positive, you get concave up. If you have a situation where the second derivative is negative, you have concave down. Okay, and I think the last definition is about points of inflection. So a point on a curve is called an inflection point if f is continuous there and the function changes from concave up to concave down, or from concave down to concave up. This can only occur when the second derivative is 0 or does not exist. Okay, so again, it's kind of related to critical points, only I want to point this out. Unlike critical points, inflection points, the sign of the second derivative must change. So look at it says that an inflection point is if the function changes from concave up to concave down, or from concave down to concave up. So if you figure out where the second derivative is 0 and it doesn't change from concave up, say it goes concave up to concave up, that's not an inflection point. An inflection point, the second derivative has to change there. The other thing is, f has to be continuous there. So it's not good enough for a function to have a jump discontinuity or something. So to be an inflection point, not only do you have to have one of these two things happen, that the second derivative is 0 or doesn't exist. So that'll give you a list of possible points of inflection, but also it has to, the second derivative has to change from positive to negative or negative to positive, and on top of all of that, it has to be a place where f is continuous. So if you have all three of these things, then you have a point of inflection. So let me give you just a quick demonstration of that. So here's a situation where the second derivative is 0, okay, and it goes from concave down to concave up. So this is definitely an inflection point. Good for us. Here we have a situation where you have this graph. Here the second derivative is 0, but you go from concave up on the left-hand side to concave up on the right-hand side. This is not an inflection point. Here you have concave up, and the second derivative here does not exist. Okay, it's got like a vertical kind of slope thing. The second derivative doesn't exist here, and it goes from concave up to concave down. That means it is an inflection point. Also notice that the function is continuous here, right? There's no jumps or anything, so this is okay. The concavity changes and it's continuous, that's fine. Over here, the derivative does not exist here, but it goes from concave down to concave down. So this is not an inflection point because it didn't change from one type of concavity to the other. Okay, so you have to be kind of aware of that kind of stuff when talking about inflection points. Second derivative test. So we talked about the first derivative test, where if I knew I had a critical point, say I have a critical point C, this is my critical point C, and I was able to calculate the first derivative on the left, first derivative on the right, and I could see that it was negative and then positive, then I would know if it's an absolute max or min, or sorry, a local max or min. This is another type of test that will allow us to know, hopefully, whether or not it's a local max or min. If I know that my function is continuous there, and the derivative equals 0, so it's a critical point, and I know that the second derivative is bigger than 0, that will mean it's concave up, right? Which means, yeah, the critical point was sitting right at the bottom. If I know that it's concave down, the second derivative is negative, then that would be a situation where here's my C, here's my critical point, and I have a function that's concave down. Oops. That's not a very good critical point. I have a function that's concave down. That would mean, see, it's concave down, that would mean that this was a maximum. However, if the second derivative happens to be 0, then I get no information. I get nothing from that. So in some sense, the second derivative is a nice little test that you can do to figure out whether or not you have a local max or min. However, it won't always tell you if you have a local max or min. It's quite possible that the second derivative is 0, in which case you're going to have to go back and use the first derivative test, see what's happening on both sides of the critical point as far as the first derivative is concerned. Okay, so in some way the first derivative test is a much more general test than the second derivative test. However, this is good if you want to use it and you're able to use it. So this brings us to probably one of the biggest, at least at this stage of your careers, the biggest use for calculus and derivatives is curve sketching. So the general procedure for curve sketching is as follows. Find the domain of your function, find the x and y intercepts, find if there's any symmetry. So we haven't really talked about this, but maybe you have in your class a little bit. The idea that if your function f of negative x is f of x, that's even. And if f at negative x is negative f of x. That's odd. Okay, so you can use some ideas about symmetry to help you out if you can. Asymptotes, so you need to check your vertical and horizontal asymptotes. Then you do the intervals of increase and decrease. So this involves the first derivative. That'll hopefully give you some idea about local maxes and mins. Then you do your concavity, so this is the second derivative stuff. And finally, at the end of the day, with all those pieces of information, you can sketch your function. So I have two examples of functions that we would like to sketch in my examples. I think what I'm going to do is I'm going to do certainly the first example, and then I'm going to move on to other topics. But I do have a second example ready. If we happen to have enough time, I'll come back and do the other example, because it's hard to get one sketching problem that incorporates all of the kind of features that you would want to see. So let's just do this one first, and then if we have time, we'll come back and do the other one. So sketch y equals x squared plus x minus x. So this one's kind of a weird one. So let's start out with the first thing that we need to do. So step one, always step one, find the domain. Okay, so the domain of this function. So for domains in general, the domains are all the real numbers except for places where denominators equal 0 or square roots are negative. So there's no denominators in here, so we don't really have to worry about where the denominator could be 0. But what we can do, what we have to watch out for, is maybe there are some places where x squared minus x is negative. So what we would like to do is we would like to know where x squared plus x is smaller than 0. We want to exclude these areas from the domain. So what does that mean? We have essentially that x plus 1 is smaller than 0. So what values of where can this happen? Well, we should split up this situation in. What we're going to do is we're going to look at the values of x and x plus 1, and we're going to split up our domain into places where this could possibly change sign. So we're going to split it up into regions or places where these factors are going to be 0. So we'll do negative infinity to negative 1, because it can change at negative 1, and then we'll go from negative 1 to 1. Sorry, negative 1 to 0, because it can change when x is 0, and then we're going to go from 0 to infinity, because after 0 it can't change at all. Okay, so when we have a really negative number like negative a trillion, x is certainly negative. When we have a very negative number like negative a trillion, x plus 1 is certainly negative. So that gives us an overall positive. So this is an okay region. This is an okay region to put numbers into here. We'd be okay in that situation. Now between negative 1 and 0, so maybe like negative a half. Negative a half, this x is going to be negative because it's negative a half. X equals negative a half plus 1 is a positive, so it's positive a half, so things in this region are positive when you have x plus 1. So our function in this region, our function in this region is going to be negative, so this is not okay. We can't use numbers from this region in this function, otherwise we'll get a negative square root. And what about really big numbers, like a million? Well, if you put in a million, x is certainly positive, x plus 1 is certainly positive, so this is positive, this is okay too. Okay, so the only real region we have to watch out for is this region here. So our domain is x in all the real numbers, but actually let's write it this way. Let's write it this way. Domain is negative infinity all the way up to negative 1. We'll talk about what we should do on negative 1, and then all the way from 0 to infinity. Okay, and now let's talk about these endpoints. Do we want to include negative 1 or not? Well, if we put in negative 1 up here, negative 1 squared is 1, minus 1 squared to 0 is okay, so negative 1 is totally okay to throw into our function. What about 0? 0 squared plus 0 is 0, square root of 0, totally okay, so we can include 0 into our domain as well. So this is our domain. So you can see there's a piece missing from our domain. Negative infinity to negative 1, and then we skip over all the numbers from negative 1 to 0, and then we continue on our merry way. So we're going to have to keep that definitely in mind when we're doing any sort of stuff about concavity and all that kind of stuff. All right, step 2, find x and y intercepts. Step 2, x-intercept. So the x-intercept, this is when y equals 0. So what we would like here is square root of x squared plus x. Oops, so that's all under the square root minus x. We would like that to equal 0. So I get x squared plus x equals x. And this is in the square root. And I can square both sides. It's going to be x squared plus x equals x squared. Okay, these x squareds cancel out. So I get x equals 0. So what value of x, what is the only value of x that actually, if I plug into my function up here, I get y equals 0. This means that the x-intercept is the point 0, 0. Next, what should we do about the y-intercept? All right, y-intercept. The y-intercept happens when we plug in x equals 0 into our function, and if we plug in x equals 0 into our function, we get 0, 0. So plug in x equals 0, we just get 0, so no big deal. The x-intercept is the same as the y-intercept. Okay, so we have those 2 points. Cool. All right, next, what's the next step? Symmetry. All right, let's see if there's any symmetry in my function. So what I would like to explore is f of negative x is equal to, so just so we're clear, I should probably have said that I'm going to say f of x is equal to the square root of x squared plus x minus x. Okay, that's what I'm going to call f. That's my function. That's the thing I'm trying to graph. So let's put in negative x into my function. Okay, this is the square root of negative x squared plus negative x minus negative x. Okay, all I did was I replaced all the x's in my function with negative x's. Let's see what happens. This is equal to the square root of x squared minus x plus x. Now let's take a look at this. Before that, I'm just going to make sure that people don't think that this little thing, I guess it's all together. This is equals. This is not less than or equal to. This is equals. Okay. So let's take a look at this. So here's my function when I plug in x equals negative x. So I plug in negative x in my function. Does this look exactly the same as the function we started with? And the answer is no. Okay. There's nothing we can do to kind of manipulate this to look exactly like our function. Also, does this look like the exact negative? Well, what would the exact negative of our function look like? It would appear that there would be a negative square root here, and this would be a positive. But there's no way to rearrange this to get a negative out here, and this positive looks okay, but there's no way to get a negative out here. Even if we factored some stuff, there's no way to do this. So this has no symmetry. Okay, because the whole idea of symmetry is I should be able to, after I've plugged in negative x, does my function look like the way it started, or does it look to be the exact negative of the way I started? And none of these are true for me, so no even, no odd symmetry. Okay, cool. No symmetry. What's step 4? Step 4 is asymptotes. So let's first take a look at horizontal asymptotes. Horizontal asymptotes. So horizontal asymptotes are the limit as x goes to infinity of my function, and we have a situation here where if we looked at the limit as x goes to infinity of this, this looks like infinity minus infinity. We might be inclined to use L'Hopital's rule. Outside of that, we could actually use that trick that we did for those of you that were with me earlier this morning. And what we can do is we can multiply and divide by the conjugate of this. So this is actually the limit as x goes to infinity of the square root of x squared plus x minus x times square root of x squared plus x divided by square root of x squared plus x plus x. That will give me the limit as x goes to infinity of, when I distribute all this kind of stuff out, of course I have to remember that this is all over 1. When I distribute all this stuff out, I get x squared plus x minus x squared all over the square root of x squared plus x plus x. And what that ends up giving me is the limit, as, so the limit as x goes to infinity of, these x squareds cancel out, x over the square root of x squared plus x plus x. Okay, and now what we do is we multiply and divide by the largest power of x. And the largest power of x in this question, as we discussed earlier this morning, it looks like it's x squared, but it's not. It's x to the power of 1, because remember this x squared is inside of a square root. So it's x to the power of 1. So I'm going to divide, multiply and divide both sides by x to the power of 1. So that becomes 1 over, I divided by 1 over x, square root. The x squared goes to 1 plus 1 over x plus 1. So as I take the limit as x goes to infinity, this goes to 0. And what I'm left with is the limit as x goes to infinity of this is 1 over the square root of 1 plus 1 is a half. So there is a horizontal asymptote at x equals a half. Okay. Now, let's take a look at the limit. Let's see what happens as x goes to negative infinity of f of x. As x goes to negative infinity, what we find here is the limit. So same kind of procedure. And what we get when we multiply the top and the bottom by the conjugate is the exact same thing that we had up here. So we have the x is going to negative infinity of x divided by the square root of x squared plus x minus, or plus x. All right, so now we have to be a little bit careful, because now we're going to negative infinity. So yes, we're going to multiply and divide, or we're going to divide the top and the bottom by 1 over x, the largest power of x. However, we have to be very, very careful, because we're going to x equals negative infinity. So let's be very careful. Essentially, dividing the top and the bottom by the largest power of x is the same as multiplying the top and the bottom by 1 over x. This is exactly the same as dividing by the largest power of x. So I'm going to multiply the top by 1 over x, and I'm going to multiply the bottom by 1 over x. X squared plus x plus x. Okay, now 1 over x, x divided by 1 over x, that's no problem. That's 1, like we had up in the previous page. That's just going to be 1. Now, where we have to be really careful is what's happening down here. When I multiply 1 over x into this square root, we have to remember that the x values that I'm talking about are negative values. So this thing out front of the square root is a negative number. It's very, very small, right? It's like 1 over what, like a really, really, really big negative number. This is a really small number, but it's still negative. 1 over negative a million is a very small negative number. So we have to make sure that when we pass through, when we put this 1 over x inside the square root, we leave the negative out front. If we actually just pass this through, it would change the sign of the square root from a positive to a negative, which is not consistent with the fact that there is a negative number being multiplied on the square root. So this ends up being negative the square root of, when the 1 over x comes inside, no big deal. It's just like we had before, 1 plus 1 over x. 1 over x times x is just 1, and so we have this. And now let's take a look at what happens here. As x goes to infinity, this definitely goes to 0. However, now we have negative the square root of 1 plus 1. This goes to 0. And this is positive, so this actually is positive infinity. So there is no horizontal asymptote as x goes to negative infinity. We might have been inclined to think that it would act exactly the same as before, but remember, whenever you're multiplying numbers against square roots, you really have to be careful of their signs. All right, so that's the horizontal asymptote. Let's talk about vertical asymptotes. Vertical asymptotes. All right, so now we have to be concerned about where things can blow up. So let's go back to our domain. Our domain is everything except for this kind of region in between -1 and 0. So what we're going to do is we're going to see what happens as I take my limit of my function as x goes to -1 to see what happens as we get closer and closer to this boundary region. And I'm going to do the same thing from the right of 0. Okay, so the limit as x goes to -1 from the left. So I'm seeing what happens to my function when I get closer and closer to this boundary. Does anything weird happen as I get closer and closer to the boundary of -1 of my function? And if I look at this, it's actually going to be pretty simple. If I'm plugging in numbers that are getting closer and closer to -1, I can just actually, -1 is in the domain of this function, so I can actually plug in -1 into this, and this ends up giving me the limit of 0, because I can just plug in -1. Same if I look at 0 from the right of my function. If I see what happens as I take 0, or I take my x closer and closer to 0 from the right, and take a look at what this limit is doing, I can just plug in x equals 0 into my function because 0 is in the domain of this function. So what do I get? I just end up getting 0. So it appears that there are no vertical asymptotes, none. Right, there's nothing weird going on. There's nothing kind of blowing up as you get closer and closer to a number or anything, so we have no vertical asymptotes. All right, so next step. Asymptotes are done, intervals of increase and decrease. So I am going to need to calculate the, what step is this? 5. So this is increase and decrease. Let's calculate the derivative of prime of x is equal to, let's take a look at what the actual function looks like. It looks like this, which is exactly equal to, if I really want to write this in this way, x squared plus x to the power of 1/2 minus x. So when I take the derivative, it's going to be the 1/2 comes down, and you get x squared plus x, then -1/2 times the derivative of the inside. The derivative of the inside is 2x plus 1, and this is going to be a -1. So the derivative is going to be 1 over 2 x squared plus x squared plus x to the power of 1 -1/2 times the derivative of the inside, which is going to be 2x plus 1 plus this derivative of x, which is just 1. Okay, so let's just simplify this a little bit. We have 2x plus 1 over, that's good, times 2, and this is an x squared plus x to the power of 1/2 down here, and plus I'm going to want a common denominator between these two, so eventually I can just multiply by 2x squared plus x to the power of 1/2 over 2x squared plus x to the power of 1/2. So now I can combine these two things into one object. So actually, maybe no, that's good. So that's the derivative. I don't know if I can simplify it. Check my notes, see if I can simplify it any further. I don't think I can. So, sorry, was that -1? -1, not plus. This is -1. Guess this becomes 2x. Yeah, I feel like something has gone wrong here. One-half. No, I think this should be fine. Okay. So, let's just leave it like this. Actually, maybe, okay. So that's my first derivative. Okay, so let's check out intervals of increase and decrease. So I'm going to want to figure out when I'm going to have to analyze this for when the derivative is positive and when the derivative is negative. So f prime of x is equal to actually, that's really disturbing. Huh. All right, perhaps I've done something wrong somewhere, and this might be simpler. But so be it. Let's actually just take a look at this, perhaps without a diagram. So let's look at what f prime of x is. So here's f prime of x. It's 1/2 times negative 1/2 2x minus 1. Now we can rewrite that as 2x plus 1 over 2 times the square root of x squared plus x, and subtract off 1. Now, the question that I have is, whenever this part is larger than 1, the derivative is going to be 0. Sorry, the derivative is going to be positive. Whenever this part is smaller than 1, then the derivative is going to be negative. So what we would like to do is we'd like to figure out when this function is smaller than or equal to 1. So let's take a look at our domain. Our domain is negative infinity to negative 1. So let's see what happens on negative infinity to negative 1. So the one thing we have to ask ourselves is this ever going to change sign? Am I ever going to get a 0 out of this? Is it ever going to change from negative to positive on this domain? So let's just look at this first part, negative infinity to negative 1. So we're talking about when we have x equals negative 1, for example. When x equals negative 1, we have negative 1 in here. So we have negative 2 plus 1. That's negative 1. And then we have on the bottom, we have some sort of 2 times. This is going to take a little bit of analysis. So when, this is why this is a little bit more complicated problem than you've probably seen in a lecture. Okay, so when x is equal to negative 1, f prime of x is equal to 2 times negative 1 plus 1 over 2 times the square. So this, so usually what you would be doing here is finding your critical points and putting everything into a plot, or into a graph that tells you increasing and decreasing intervals. The problem with this question is it's very difficult to actually solve for when this is equal to 0. Perhaps we can do it. Yeah, perhaps we might as well just do it that way to see if that's not how I did it in my notes, but maybe we could just do it that way, and things will work out okay. If not, we'll abandon this question. And I'll write it up in the notes. And yes, for those of you that are asking, I will be able to save these notes and email them to everybody. So once I get a good working example that works properly, then I should be able to get it out in a way that you can actually understand. So let me just erase this. And let me just do it the old-fashioned way without any sort of fancy analysis. Let's see if I can just figure out the critical points and go from there. If not, then I think we'll move on, and then I'll write it up for you so you can see, and then email it to everybody. Okay, so let's figure out, this is my function, so f prime of x is equal to 2x plus 1 minus 2 times the square root of x squared plus x over 2 times the square root of x squared plus x. Okay, so we would like to know when is this equal to 0. So we would like to find our critical points. So when does this equal 0? On the domain, this part of the domain, for any of these like really large negative numbers, this is always going to give me a positive number. There's no area that this will actually end up being a problem. So this is always going to be a positive number on the bottom. So this can only be a derivative. So where does this derivative not exist? The derivative wouldn't exist at a location, for example, x equals 0. So f prime, so x equals 0, f prime of x does not exist. Right, because we plug in x equals 0 into this, what do we get? We get 0, and we get 2 times the square root of 0, which is 0. So the derivative does not exist at x equals 0. However, x equals 0 can't really be a critical point of our function because it's actually on an endpoint. Just like we were doing absolute max and mins, it's actually on the endpoint of an interval. So this really doesn't qualify as but not a critical point. It doesn't really qualify as a critical point because it's on the endpoint of an interval. So let's see when else this would equal 0. So the only other time that this would it exists everywhere else for any sort of x that we want to plug in that's in our domain. So the only other time that we can get a critical point is if the denominator or the numerator equals 0. So let's figure out when the numerator can equal 0. So let's figure out when f prime of x equals 0. That'll happen when 2x plus 1 minus 2 times the square root of x squared plus x. Thank you for those of you who are checking Wolfram Alpha for me. Let's see if this will work. Perhaps I can show you why Wolfram Alpha is correct. If I move this to both sides, I get 2x plus 1 equals 2 times the square root of x squared plus x. If I square both sides, I get 2x plus 1 squared equals 4 times x squared plus x. Okay, so then if I actually carry this out, I get 4x squared plus 4x plus 1 equals 4x squared plus 4x. Okay, so now if I actually try to solve this, what do I end up with? I end up with 1 equals 0. So no solution. So thank you, Wolfram Alpha. There is no solution. All right, so there's no critical point. X equals 0. There's no place that f prime equals 0. So there is no critical point. So there is no place that this is going to change from increasing to decreasing. So essentially all we can do now is, these are all one big interval. So this would be one interval. It'll either be increasing and decreasing on this whole thing, and it'll either be increasing or decreasing on this whole thing. So we can just take test points. For example, negative 1,000,000. What's happening to our derivative at negative 1,000,000? At negative 1,000,000, this thing is positive because I have negative 1,000,000 squared. Square root is positive. 2 times negative 1,000,000. This is really negative. This is really positive. And then 2x plus 1. Let me see. And negative 1,000,000. This is going to be smaller than x squared. So the square root is going to be smaller than x squared. So this is end up going to be negative. So f prime of x is less than 0 on the interval negative infinity to negative 1. So that's the first interval. There are no critical points, so it has to be the same sign on the whole area. And f prime of x is, let me see what happens on the other interval. When we get really positive numbers, really positive numbers are going to give us a situation where the derivative, this is going to be a positive number again. The derivative is going to be positive because this is going to be a positive number in here. X is going to be a positive number. X squared plus this thing under the square root is going to be bigger than 2x, than x squared, which means the square root is going to be bigger than x. So I think this should be positive. So with a little bit of thought, I think that perhaps I didn't present this totally well, but with a little bit of thought, this should be positive. It's increasing on this. All right, this was not really a good example to do, I don't think, but whatever. We're kind of halfway through it now, so we might as well finish it. Sorry for that. Part 6, concavity. Okay, so let's take a look at our derivative. Our derivative is right here. Oh man, what a mess. Okay, our second derivative. So let's do concavity. Again, I apologize for this. I wanted to pick a more confusing example because I wanted to show you a really good example, but of course it's quite complicated, so you wouldn't probably see something this complicated on exam. So let's look at concavity. So we want the second derivative of x. So let's look at f prime of x. And I have calculated this already, and in the interest of time, I'm just going to write down what the second derivative is. Negative 1 4x squared plus x to the 3/2, I think is what it should be. Okay, and if you look at this now, this number down here, when x is positive, sorry, no matter what x is positive or negative, this thing down here is always going to be a positive number. Of course, negative 1 is going to be a negative number, so f double prime of x, the concavity is always going to be negative, so it's always going to be concave down. So it's going to be concave down, concave, on domain. Okay, because no matter what numbers we plug in for our from our domain, we can always, no matter what numbers from our domain go in here, we can always see this is going to be a very large, there's going to be a positive number on the bottom, and so it's always going to be a negative number. There's no way that you can make this, there's no inflection points, there's no places that this equals 0 or doesn't exist other than x equals 0, which doesn't qualify. So at the end of the day, you have a function that is concave down everywhere. Okay. So this is kind of a non-standard example, but that's it. So let's sketch. So no inflection points. So let's just sketch. So what information do we know? We know that certainly the domain, so we have this gap between negative 1 and 0. There is the xy intercepts are 0, 0. What else do we know? No symmetry. There's one horizontal asymptote on the right. The horizontal asymptote on the right is x equals 1/2. There is no horizontal asymptote on the left. It is decreasing on the first part. It is increasing on the second part. And I think one other thing that I might want to know is this decreases all the way down to the value at x equals negative 1. So let me see what the value of the function is at negative 1. F at negative 1 is, it decreases all the way to negative 1. So I just want to kind of plug this in to see what the point's going to be. Negative 1 is going to be negative 1 squared is 1 plus negative 1. So that's square root of 0. Negative negative 1 is 1. So I think f at negative 1 is 1. And I think that's all the information we need. So let's sketch this now. After a long time on this problem, let's just sketch it, see what we get. Okay, certainly, let's check out our domain. So negative 1 to 0, there's nothing that can happen in here. We know that there is a x and y intercept there, and we know that at x equals 1/2, there is a horizontal asymptote. So this is x equals 1/2, or y equals 1/2. We know it's concave down and increasing forever and ever and ever, so we know that this should look like something like this. It shouldn't cross the asymptote. I can't really draw with this thing very well. And negative 1, it was, as we went to negative infinity, this went to infinity. So we've got, it went down all the way to, what was our function at negative 1? It was 1. So here is the point y equals 1. So there's the point y equals 1. It comes all the way down to there. And it's always concave down and decreasing, so maybe something like that. I think that would be about it. So yeah, sorry about that example. It was a little bit more non-standard analysis than I wanted. But if this was more of a standard problem, all this kind of stuff that we did with symmetry and asymptotes, that's all okay. This increasing, decreasing stuff was a little bit tricky. Usually what you're going to get is the stuff that you've seen before, where you get the first derivative, you figure out what the critical points are, and then you make your nice little table where you split everything into intervals, and you can figure out on which interval things are positive or negative. But this required a little bit more thought and a little bit more analysis, so this is probably a little bit too hard. But at the end of the day, again, you see kind of what the ideas are behind sketching. Okay, so let's skip this one. Maybe we'll have some time to come back to it. It'll probably be a better example. And let's kind of move on. Let's do optimization problems. How many optimization problems do I have? I have a few optimization. Yeah, let's do the optimization problems, and then we'll take a little, maybe a 5-minute break, and then we'll get back to it and finish up. So, optimization problems, super simple. The idea behind an optimization procedure is usually what you do is you want to draw a picture of what you're trying to optimize. And then this is the only real thing, this is the only real difference that I was talking about before, that you are in charge of making a function for what it is you're trying to optimize. So Q is something like I want to optimize the volume, so Q would be the volume, or this is whatever quantity you want to optimize. So this is your responsibility. So this is the hard part about optimization problems. Once you've kind of once you've figured out what the function is you're trying to optimize, then after that it's just pretty much an absolute max and min problem. So, you know, find your critical points, plug in the critical points of the values, and then also calculate the values on the endpoints if you have them. And yeah, it's just an absolute max and min problem. So the real hard part is figuring out what Q is. So we're going to do a couple of those. The only thing I do want to mention is because this is a single variable course, you will never have to optimize any functions that have more than one variable in them. And what I mean by that is, you know, you always have functions of one variable. If you have a function that has more than one variable, for example, if you were trying to optimize the volume of, say, a cone, which we've seen before, 1/3 pi r squared h, this has two variables in it, r and h. So if you were trying to optimize or maximize the volume or something, you wouldn't be able to maximize this until you somehow got rid of one of the r or h's. And in the situation we saw a couple questions ago, we were able to figure out what the relationship between r and h was, so we could get rid of the r's and have only a function in terms of h. So don't optimize, don't do your absolute max and min test or your absolute max and min problem until you've eliminated all of the other variables except for one variable in your function. That doesn't always happen, but sometimes it does, so you want to be prepared for it. Okay, so let's do an optimization problem. Find the points on that ellipse that are farthest away from the point 1, 0. Okay, so let's draw an ellipse. So, as always, you want to sketch this problem. This is an ellipse. What the ellipse, I mean, in this case, the sketch isn't super important to be super accurate, but you kind of want to get the idea of what's going on. What is some point on the ellipse so that it is the farthest away from the point 1, 0. So here's the point 1, 0. Okay, and you want to find what point on this ellipse is the furthest away from here. So let me maybe draw a point here. This is my point x, y, and this is my distance, and I want to figure out what point on the ellipse is the furthest away from 1, 0. Okay, so let's get started. Let me see if I can check my notes. So this distance is what we're trying to optimize. So this is the Q that I was talking about, this distance here. And what I can actually do is just using some, let me see. So this is the point xy my ellipse. So the distance between this point 1, 0 and my point on my ellipse is d squared by Pythagorean theorem is x minus 1 squared plus y minus 0 squared. Okay, so this is just Pythagorean theorem, so the distance between these 2 points, which is equal to x minus 1 squared plus y squared. Actually, maybe I just want to expand that out a little bit. Equals x squared minus 2x plus 1 plus y squared. So this is my distance. It's a kind of a well-known fact that optimizing the distance is the same as optimizing the distance squared. So what I'm going to do in this case, you can, if you want, calculate d by just taking the square root of all this. I don't want to. It's easier to work with d squared. Maximizing distance is same as maximizing the distance squared. So I'm going to call this S for the square distance. So rather than maximize the distance, which you can, you'll get the exact same answer. If I mean, for a long time I preferred to just deal with the square roots, but today I'm just going to show you a method where you don't actually deal with the square roots. Instead, I'm going to say that this is my function S, and I would like to maximize it. It's the square of the distance. Maximizing the square of the distance will maximize the actual distance. So let's just maximize this function. As I mentioned before, there's no way we can do this question because, well, there's two variables. So our distance squared, our S function, is a function with two variables in it, x and y. However, I can use some of the constraints, or one of the constraints, to make sure that I only have one variable, and that is, if I look up over here, my point has to be on the ellipse, which means my point has to satisfy this equation somehow. Every point on the ellipse will have this relationship between x and y, which means if I rearrange this, I can see that y squared has to be equal to 4 minus 4x squared. So any point on the ellipse, its y value squared will be equal to this. So certainly any point that I'm trying to find on my ellipse will also have that true about it. So if I plug in 4 minus 4x in for y squared, I get plus 4 minus 4x. And if I rearrange this, x squared minus, sorry, this is x squared. X squared minus 4x squared is minus 3x squared. And then I have minus 2x plus 5. So I think this is the function that I would like to maximize. So now this is my function. Now it's just a simple max and min problem. So let's find critical points. So the derivative of s with respect to x is equal to negative 6x minus 2. So this exists everywhere. So certainly there is no place where I can plug in x and I don't get a number. So this derivative exists everywhere. So that part of the critical points I'm not going to get any information from, but I can calculate when ds by dx equals 0, or s prime equals 0. This is another place that I get my critical points from, and I get 6x plus 2 has got to be equal to 0, which means x equals negative, let me do that again, 6x plus 2 has to equal 0, which means x has to equal 1/3. Okay. Now I can take, now what I do is I can, into my distance equation here, I can plug in my critical points so that I only have one critical point. So plugging in my critical point, s at 1/3. So what is, when x equals 1/3, how far am I away? What is the distance squared from the point 1, 0? It's negative 3 times 1/3 squared minus 2 times 1/3 plus 5. If I do this, this is negative 3 over 9 minus 2. Let's do that as negative 3 over 9 minus 4, minus 6 over 9. That's minus 2/3 plus 15 over 9. I just did this so it's all over 9, just so I can do an easy calculation. Negative 3 minus 6 is negative 9 plus 15 is 6 over 9, so the distance is 6 over 9, which is equal to 2/3. Sorry. Negative, thank you, negative 1/3. People, the kind people in the chat. Negative 1/3. Sorry, that's going to change some things. Negative 1/3. Negative 1/3. So I'm going to erase this. Okay. All right, so this becomes negative 3 times negative 1/3 squared, so that becomes 1/9, negative 3 over 9. Negative 2 times negative, this becomes positive 2/3, which becomes positive 6 over 9, and then that becomes plus 45 over 9. Is that right? I think so. Okay, so negative 3 over 9 plus 6 over 9, that's 3 over 9 plus 45 over 9 equals 48 over 9. Which is 16 over 3. Okay, good. So that's my value at 1/3. Now, what are my endpoints? So, my endpoints. What is the smallest value of x I can get, and what is the biggest value of x that I can get? Okay, so the smallest value of x that I can get is right here. Sorry, the largest value of x that I can possibly be at is at this point here. So this the vertex of the ellipse here, and the other version of x, or the other end point of my interval is over here. So we have to figure out where these two endpoints are. So they happen when when y equals 0. So let's go here and do endpoints. Running out of room, but endpoints happen when y equals 0. So when y equals 0, that is 4x squared equals 4. So the endpoints happen when 4x squared equals 4, which means x squared is equal to 1, which means x is positive or negative 1. So let's see what happens when we plug in positive 1 into our function. We get negative 3 times 1 minus 2 times 1 plus 5. That is equal to negative 3 minus 2 plus 5 is 0. And s, the other point, is negative 1. That becomes negative 3 times negative 1 squared minus 2 times negative 1 plus 5 equals 0. And that is negative 3 plus 2 equals negative 3 plus 2 plus 5, and that is equal to negative 3 plus 2 is negative 1, 4. Okay, so now we have to figure out which one of these points, our critical point, has the largest distance. So our largest distance happens when s equals negative 1/3, so I should change this to negative 1/3 as well. When we had x equals 1/3, this was the square of the distance, 16 over 3. When we had x equals 1, we had 0. And we had s equals negative 1, we had 4. So which are the largest of these? The largest of these is this, when this happens. So largest distance when x equals negative 1/3. And when x equals negative 1/3, there's two versions of y. So when I plug in x equals negative 1/3 in here, I can figure out what the two numbers for y are, and then I can figure out that's the point. But we'll just leave it like this. So the largest distance occurs when x equals 1/3, and the largest distance squared is 16 over 3, which means the largest distance is the square root of this, which is 4 over the square root of 3. Okay, so let's do one more optimization problem, and then we'll take a break, because I certainly need one. This one is kind of an interesting problem. Let V1 be the velocity of light in air, and V2 be the velocity of light in water. According to Fermat's principle, a ray of light will travel from point A to point B by a path A, C, B. So it follows this kind of pink arrow and then this blue arrow down to B. And the path that it follows minimizes the time it takes to go from here to here. So the velocity of light in air is different than the velocity of light in water. So this is how it goes. And then show that sine theta 1 over sine theta 2 is equal to V1 over V2. This is called Snell's law. You may have seen it in your physics classes, but this actually comes from an optimization problem. So let's see if we can do it. So the idea is, let's rederive Snell's law by using our ideas of optimization. So we want to minimize the amount of time it takes for light to go from A to B. Okay, so this distance from this point here to this point here, I'm going to call x. This whole thing I'm going to call, from like the whole vertical distance or horizontal distance from A to B, I'm going to call d. So this is d minus x. in there. Let's see if I can write that better. D minus x is in there. And so what I would like to do is I would like to figure out how much time it's going to take to go from A to C, and then how much time it's going to take to go from C to B. I'm going to add those together. So t. So what is the time as a function of x? Well, how long does it take to go from, and I think what I'll do is I'll also call this height little a, and I'll call this height here little b. Okay, so what is the total amount of time that it's going to take as a function of x? So the total amount of time as a function of x is going to be, this by Pythagorean theorem is going to be the square root of a squared plus x squared. So it's going to be this distance, a squared plus x squared, divided by how fast is the light traveling in the air. It's traveling at velocity v1. And then how far of a distance is it from C to B? It's the square root of b squared plus d minus x squared. And that's all speed v2. Okay, so with that done, now what I would like to do is I would like to, the idea is I'm going to figure out what is the optimal x that makes this the fastest. And once I kind of figure out that optimal x, I'll be able to figure out a relationship between the theta 1 and theta 2. So let's, this is the function that I would like to optimize. This is the total amount of time that it takes for a light ray to go from A to B. So I would like to optimize this. So I'm going to take the derivative, so t prime of x. So now it's just an optimization problem. This is the function I'm trying to optimize. Now it's just a straight optimization problem. If I take this derivative, what do I get? I get the derivative of this is going to be 1/2 a squared plus x squared to the negative 1/2 times the derivative of the inside, which is 2x, and that's all going to be over v1 plus, now this derivative is going to be 1/2 b squared plus d minus x squared to the power of negative 1/2 times the derivative of the inside. The derivative of the inside is going to be 2. The derivative of this inside is going to be 2. The 2 comes down, you get d minus x times the derivative of the inside of that, which is negative 1. So it's going to be 2 times d minus x, 2 times d minus x times negative 1. Okay, so this 2 cancels out with that 2, and what I end up with is 1 over v1 times x over the square root of a squared plus x squared. Okay, that's that part. Plus, let's simplify. Oh, sorry, this is all over v2. Okay, let's figure this out. This is 1/2 times, this is all under the square root, b squared plus d minus x squared. So that's that square root part brought down. And on the top, I have negative 2d minus x. So these 2's can, these 2's can cancel, and what I get is 1 over v1 x over the square root of a squared plus x squared minus d minus x over the square root of b squared plus d minus x squared. Okay, so now I would like to, so this is the derivative. So where can I possibly, what's the optimal solution here? The optimal solution is at either critical points or endpoints. So if we let, the first thing we need to do is calculate our critical points. So we take a look at when this this derivative can be does not exist. So this derivative does not exist. Where would there be values where this doesn't exist? Well, x is always positive. right? So x is always, oh, sorry, someone corrected me. There's a v2 in here, thank you. Times 1 over v2. Okay. So, where can these derivatives not exist? Any value for x that you plug in here will always give you a positive number. This is always going to be a positive number, so you don't really have to worry about that being a problem. Over here, I guess you could have maybe x is equal to d and you have a 0 down here, but at the end of the day, because of this b squared, there's never going to be a problem with plugging in x values into here. So the only place that we could really have a derivative that is not, or a critical point, is when this thing is equal to 0. So what I'm going to do is I'm going to set this equal to 0. Set to 0. And that means that I have 1 over v1 times x over the square root of a squared plus x squared is equal to d minus x over the square root of b squared plus d minus x squared times 1 over v2. All right, so that's fine. Let's take a look at this. So if we go back up to our diagram, here's theta 1. What is x divided by a squared plus x squared? This diagonal is the square root of a squared plus x squared. So x divided by this is the same as the opposite over hypotenuse of this theta 1. So this thing sitting out right here is sine of theta 1. So this ends up being sine of theta 1 divided by v1. Okay, so now let's look at the other one. Same thing over here. This is the hypotenuse b squared plus d minus x squared square rooted. And this is the opposite side of theta 2. So what do we end up with here is theta 2, or sine theta 2 over v2. And this is precisely what we wanted to prove. This is Snell's law. Now, the next thing we could do is we could figure out whether or not we might want to say, well, what about the endpoints? So a little bit of analysis will show you that this is the actual minimum. This is the angle that, or the x that minimizes the time, is given by this. And you can actually show that this actually is a minimum by doing a second derivative. If you do the derivative with respect to x, you'll be able to convince yourself that this is using the second derivative test, and that this is actually a minimum. I don't really have time to go do that all here, but this is how you would use optimization to solve Snell's law, or to rederive Snell's law. So we have about an hour and 10 minutes left. So why don't we take about a 7-minute break? I'm going to come back at 4 o'clock, and we're going to finish up the rest of this section, which is linear approximation and differentials, Newton's method, and some L'Hopital's questions. So that's what's coming up. I'll be back in about 7 minutes. Okay, let's try to get through this last hour, and then we can have some, or at least I can have some dinner. Maybe you guys can grab something too, for those of you that are coming back for the last 3 hours. So let's kind of finish off strong here, if we can. So the next kind of topic is linear approximation and differentials. The idea behind linear approximation is that if you happen to have a very complicated function, you are sometimes able to approximate this complicated function, like sine x, or you have some sort of crazy function like the one we were trying to sketch, or whatever. You can approximate it actually by sometimes by a line. So instead of taking your actual function f of x, you can actually make a different function called L of x, which is L stands for a line, which is defined this way. So it's the value of the function at a given point plus the derivative at that given point times x minus a. This is called the linearization of f at a specific point. So if you can linearize your function at x equals, or for your value of a, it might be 3, my value might be 5, and you'll come out with different equations of this line depending on where you linearize. And the idea is you would like to linearize your function near a point, so that, you would like to pick a, where you're doing your linearization around. You would like to pick it so that it's a point where you can actually calculate the function without using a calculator, but also that it's close enough to any values of x that you would like to plug in. Because if you're too far away from a, if you plug in values for x that are too far away from a, this thing can get very, very big, and your approximation will actually get worse and worse and worse the further you move away from a. So this approximation is only really good for values of x that are close to a. So again, when you're asked to figure out, well, where should I do my linearization around, you want to pick somewhere that you can actually calculate the function at that point, so it's easy to calculate, but also you want to calculate the linearization at a point that is close to points that you might want to plug in for x, because you don't want to linearize a function too far away from where you're going to use it, essentially. Differentials. Differentials are actually one of the least understood concepts in calculus, and that's okay. But they're actually quite simple once you kind of wrap your head around them. The idea is if I have some function, then I have this independent variable called a dx, is called a differential. So it's a little change in x. And if you want to be think about high school, you can think about this as delta x. It's a little bit of a change in x. And dy is the change in the dependent variable. So you can think, if you think about high school for this is the little bit of change in y, kind of. And the idea is the little change in y is equal to the derivative in the little change of x, provided this is exactly equal to, provided that your change, these delta x's and delta y's go to 0. So if you want to look at this in a high school way, this would be kind of like the little change in y, the amount that your y is going to change is approximately equal to the derivative times your delta x. So how much x did it change? Well, I went from x equals 3 to x equals 3.1. So delta x would be 0.1. I know my derivative, and I know that would give me more or less how much change in y is going to be. This is a way just to approximate things when you're out in the engineering world, or you want to know how much, if you know your function of, say, volume of a sphere depends on the radius, and you multiply the radius plus or minus 1 centimeter, you might want to know how much the error is. How much does the radius or the volume of the sphere change if I changed x by a little bit, if I change x by a little bit of error. So this is kind of what differentials are. They just tell you, really, really simple idea, they just tell you how much is y going to change if you change x in a certain way. And how are these related? They're related through the derivative. That's the whole idea behind differentials. So let's do an example here. Explains in terms of linear approximation of differentials why the approximation of secant of 0.08 is approximately equal to 1 is reasonable. So the idea here is, all right, so say I'm doing some calculation on some beach somewhere and I don't have a computer, I can just, instead of saying, okay, my calculation involves taking the secant of 0.08, I'll just say it's 1 instead. Explain why this might be reasonable. And the idea is this. Suppose I have the function secant x. What I can do is I can linearize secant. So if f of x is secant x, what I can do is I can linearize this near 0. See how secant, this 0.08 is really close to 0, right? So I can approximate secant 0.08 by perhaps a line that is linearized near a equals 0. So let's try that. So my linearization of this, according to the formula, is equal to my function at where I want to linearize it plus the derivative of where I want to linearize it times x minus a. So what a value should I choose here? Well, I want an a that allows me to calculate my value of the function. I want an a that I can plug into secant that I know the value of. Secant is 1 over cos. Certainly I know cos of 0. So how about a equals 0? That'd be a pretty good one. Why else would I think a equals 0 would be a good one? Well, because I want to plug in, at the end of the day, I want to plug in 0.08 into my formula. Well, if I plug in 0.08, I want to be close to the number that I plug into my formula. I want to be close to where I did the approximation. I'm going to do the approximation at a place that's close to 0.08. Namely, let's let a equal 0. So L of x is equal to f at 0. So actually, let's a equals 0. Let's calculate these pieces. That looks like does not equal. Let's calculate these pieces. A equals 0. So f at 0, we're going to need that part. So f at 0 is equal to secant of 0, which is equal to 1 over cos of 0, which is equal to 1. Okay, so that's good. F prime at 0. All right, so what's the f prime at 0 is what's the derivative of secant x? The derivative of secant x is secant x tan x. If you forgot that on an exam or whatever, you could, this is just secant is just 1 over cos using the quotient rule or whatever. You could probably rederive that if you wanted. Secant x tan x, so I'm going to evaluate this at x equals 0. So that's secant of 0 times tan of 0. And tan of 0 is 0, so that whole thing gets wiped out and ends up being 0. So my linearization is equal to, what is f of a? F of a is my function at 0, which was 1, plus, what is the derivative of a? Derivative of a is 0 times x minus a. So yeah, if I approximate secant x near a equals 0, if I approximate secant, I can pretty much say that anything that is, any number that I plug in that is close to 0, any number that I plug into secant that is close to 0 is approximately just 1, because the linearization is just 1. So that's why if you were stuck on a desert island and you need to do secant of 0.08, if you made it just a straight line near x equals 0, this 0.08 approximately, secant of 0.08 is approximately 1. So you're justified in using that approximation. Okay, so that's the idea behind linearization. We'll do another one. So use the linearization of f of x is the cube root of 1 plus 3x at a equals 0. What's the linearization? And use it to approximate this, 1.03. So this is actually kind of nice because they give us our function, they give us where they would like this approximated by. So f of x is 1 plus 3x to the power of 1/3. So f prime of x is equal to 1/3, 1 plus 3x to the negative 2/3, times the derivative of the inside, which is just 3. And that ends up equaling the 3 cancels out with the 3, and I end up with 1 plus 3x to the negative 2/3. So that's the derivative of my function. Now they would like it to be approximated near a equals 0. So what is my function at 0? So let me see, go back up here. If I plug in 0 into this, I get 1 to the power of 1/3. That's just equal to 1. That's good, because I can calculate the value of the function there. And the next thing I need to know is what is f prime at 0. So here's my f prime. It's right here. If I plug in 0, I get 1 to the power of negative 2/3. So again, that's just 1. So what's my linearization of this? My linearization is f at 0 is 1 plus the derivative at 0 is 1 x minus, well, where am I doing the linearization around? My a is 0. So what does this mean? This means that the function, the cube root of 1 plus 3x, behaves a lot like the line 1 plus x when I stay close to a equals, when I stay close to 0, when I stay close to x equals 0. So rather than use this function, f of x equals this cube root 1 plus 3x, instead I can just use this function, this line function, instead, as long as I use x values that are close to 0. So what does that mean? That means that I can use, if I want to calculate the square root of 1.03, that's precisely equal to my f at, well, this is 1 plus 3 times 0.1. So this is my function value at 0.01. If I took 0.01 and plugged it into my function, okay, I would get the cube root of 1.03, which is what I want. And I just told you that that function, as long as the number I plug into my function is close to 0, which 0.01 definitely is, as long as I stay close to 0, I can approximate this function by my line. So this is approximately equal to my line at 0.01, which is really easy to calculate because I just plug in 0.01 into my line and I get 1 plus 0.01, which is 1.01. So if you wanted to go on your calculator, you could actually, I mean, obviously, if you're not stuck on a desert island, you could just calculate the cube root of 1.03. But what you'll find is it's actually pretty close to 1.01. So you can use linear approximations to, rather than deal with the very large, complicated function that you want to deal with, you can replace it by a simpler function. And to be honest, you'll do this a lot of times in the next few years. You'll be replacing a lot of very complicated functions by simpler versions to do integrations and to do partial differential equations and a whole bunch of stuff. So this idea of approximating one function by another function is something that you'll probably have to do many, many times. So this is the first kind of introduction to it. Okay, so moving along. So that's linearization and differentials. Newton's method. So the idea behind Newton's method is that if I have some function and I would like to figure out when that function equals 0, what x value gives me 0, that would be right here. So here's where the function actually equals 0. What I'm going to do is I'm going to start at I'll take a guess, x1, that's my first guess, and I'll plug it into the function, and then I'll calculate the tangent line of the function at that point, and I'll follow the tangent line all the way back to the x-axis, and that'll give me a new guess. Take that new guess, plug it in the function, follow that tangent line all the way back, that'll give me a new guess. Take that new guess, plug it in the function, take the tangent line, go all the way back, and eventually the idea is if I do this enough times, I'll get closer and closer and closer to what this value actually is. And this is the idea behind Newton's method. And if you sit down and actually derive it, this is the formula. So if I would like to know when f of x is equal to 0, I would like to figure this out. What value of x does this for me? What I do is I start out with an initial guess. In the previous slide I used x1. I like to use x0, but it doesn't really matter. Then each new guess is given by a previous guess using this formula. So my next guess would be my previous guess minus the function at my previous guess divided by the derivative of my function at my previous guess. That will give me a new guess, and I just keep repeating over and over and over and over and over. So for example, x1 would equal x0 minus the function at x0 divided by the derivative of x0. All right, so I would all calculate that, and that would give me x1. To calculate x2, to calculate my next guess, I would use the x1 I just calculated in this formula. So I'd have x1 minus the function at x1 divided by the derivative at x1. Okay, so I would calculate that. Now to get, so I have a new guess, which is x2. Now to calculate my next guess, I would take the x2 I just calculated and use the formula. x2 minus f of x2 over the derivative of x2, and so on. And the idea would be, hopefully, I do this over and over and over and over and over, and my guesses get better and better and better, and I get closer and closer and closer to the actual solution. Now, this doesn't always work, but for all intents and purposes in this course it will. So this is the idea behind Newton's method. So let's take a look at an example. Of course, these examples are extremely difficult to do with a calculator, let alone without a calculator. So, I mean, it's likely you wouldn't be asked, although I can't say that for sure, but it's likely that you wouldn't be asked to carry out a full Newton's method thing on an exam, but you certainly should be prepared to do so. So let's take a look at an example. A car dealer sells a car for $18,000. He also offers to sell the same car for payments of $375 per month for 5 years. What monthly interest rate is the dealer charging? To solve this problem, you will need to use the formula present value consisting of n equal payments of size r with an interest rate of I per time period. So this is a kind of a finance example, but actually anyone who has bought a car has done this, or anyone that will buy a house. This is the equation you'll be using, at least a close approximation of it. So this is actually a real life example. Replacing I by x show that this equation is true, and then solve it using Newton's method. So the idea here is A is the amount that you essentially would like to borrow, or the amount that you need to raise. So in our example, A is equal to 18,000. Okay. In our example, R is the amounts that you're paying per month. So R in this case would be 375. The number of payments, N, is you are going to pay per month for 5 years. So that's 5 years times 12, which is equal to 60. So N is equal to 60 in our example. And I think that's all the information that we need. The one thing we don't know is the interest rate, I. What is the interest rate that they're charging per period? All right. So let's use all this information in the equation that they gave us. So this is 18,000 is equal to 375 divided by, instead of I, like they said, we're going to use x. So I is x in our case. We could leave it I if we wanted, but we're much more used to x, so let's just use x as the unknown. 1 minus 1 plus x to the power of negative 60. Okay, so we can multiply both sides by x, and we can divide both sides by 375, and what that will end up giving us is 48x is equal to 1 minus 1 plus x to the power of negative 60. Okay, and so the next thing we can do is we can multiply everything. This is a kind of an ugly term because we have 1 plus x to the power of negative 60, so we're going to multiply everything by 1 plus x to the power of 60. So this is 48x, 1 plus x to the power of 60 equals 1 plus x to the power of 60 minus 1. Then I put everything on the other side. I get 48x, 1 plus x to the power of 60 minus 1 plus x to the power of 60 plus 1 equals 0. Which is what we needed to show. Good for us. So that's the equation that they wanted us to figure out. Okay, so now that we have that, now we want to solve it. Now we want to figure out what the actual interest rate that they're charging is. So let's go ahead and do that. So we're going to use Newton's method to do that. So for Newton's method, we need the function. And one thing to keep in mind about Newton's method is you always, before you get started, have to make everything equal 0. So you need to move everything to one side and make it equal to 0. This is the function. If we left some parts over on the other hand, on the other side of the equal, we wouldn't be able to use Newton's method, or at least we wouldn't be able to use it correctly. So before you even start on Newton's method, you need to move everything over to the one side, set it equal to 0, and that is what is going to be your function. So my function is 48x, 1 plus x to the power of 60 minus 1 plus x to the power of 60 plus 1. That's going to be f of x. The other part that Newton's method needs is it needs the derivative. It needs a derivative, f prime of x. So let's actually calculate the derivative here. So this is a product rule. So it's going to be 48 times 1 plus x to the power of 60 plus 48x, take the derivative of this one, times 60 times 1 plus x to the power of 59 times the derivative of the inside, which is just 1, minus the derivative of this is 60, 1 plus x to the power of 59 times the derivative of the inside, which is just 1. So let's see if we can clean this up a little bit. We're going to factor out a 1 plus x to the power of 59. So 1 plus x to the power of 59 we're going to take out. And then on the inside, what we're left with is 48 1 plus x plus 60 times 48, whatever that is, times x minus 60. Okay, so that's the derivative, I think, if I've done everything properly, which it looks like I have, I think. Okay, that's the derivative. And so what we would do is now we're going to start Newton's method, and the big question that everybody asks me is, what should my starting value be? And the answer I always give them is, well, there's no real answer I can tell you that always works all the time. It most likely is just it's an educated guess. So for example, if I knew that I knew for sure the interest rate was between 0 and 10%, maybe I would start with my x0 being 5%. Maybe I would start, if I knew that it was a really small interest rate, maybe I would say it's equal to 1% or something along these lines. And in principle, different x values will give you different solutions, and some x values, some starting values won't give you a solution at all. So when people say, if I start with this x value and something goes wrong or I don't end up with the right answer, what do I do? Well, the answer is you just try to start the question with a different x value. In theory, in practice, obviously on an exam it wouldn't be that difficult to figure out what your starting x value is, but the idea is just choose something that's reasonable and then start your procedure. So I'm going to choose that my x0 is going to be 0.01. So this is 1%. This is a 1% interest rate. Okay, so let's start with that. So my x1, so my next guess is going to be my function at 0.01, so it'll be 48 times 0.01 times 1 plus 0.01. Okay, I'm just plugging in my guess into my function, the original version of my function, minus 1 plus 0.01 to the power of 60 plus 1. Now sorry, that's wrong. Ugh. I start with my original guess. So the formula, if you look back at what the formula says start, your next guess is equal to your first guess, or your current guess, minus, and now we plug it into our function, minus, plug in our guess into our function, 48, 1 plus 0.01 to the power of 60, plus 48, nope, my original function, 48.01 times 1 plus 0.01 to the power of 60, so I'm plugging into there, minus 1 plus 0.01 to the power of 60, plus 1, and then that whole thing divided by, that's my function when I plug in my guess, that whole thing divided by my derivative when I plug in my guess. So this will be 1 plus 0.01 to the power of 59 times, oops, don't want to move that line, times 48 times 1 plus x, oops, 148, 1 plus 0.01 plus 60 times 48 times 0.01, because that's my x, minus 60. Okay, and you can probably do this in your head. We get 0.0082202. 0.0082202. Okay, and now, yes, you're going to be very, very disappointed, but the idea, I'm not obviously going to plug this in by hand. the idea would be you would repeat this. If you have a calculator, as I've told my class, if you have a calculator that has the answer key on it, you can actually figure out how to do this where you just keep hitting answer, 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 answer. And what it'll do is it'll keep plugging in your newest answer into this formula, and eventually you'll converge on some solution, hopefully. So the idea would be we would take x2, our next guess for this would be take this value that we just calculated for x1 and plug that into the formula. So I would plug that into the formula, calculate what that answer is, and I can give you that answer. It is 0.00768. 0.0076802. And the next one, if you take that version and plug it into Newton's formula, you would get 0.0076291. 0.0076291. And finally, the next one we would get if we plug that version into Newton's formula would be 0.0077686. 0.0076286. So you can see we're getting closer and closer and closer to something, and it appears that it's at, something like 0.00762. So the interest rate, so you maybe conclude at this point that the interest rate is about, so this is per month. This is the interest rate per month. So it's about 0.7% per month, which works out to be about 9.4 for the whole year. So anyway, that's how you would use Newton's method. Of course, you do need a calculator to calculate it, but in theory, it's just a repetitive process of taking your next guess, plugging it back into the formula, getting your new guess, and repeating that over and over and over until hopefully your numbers start converging on something that makes sense. Okay, so that's Newton's method. And finally, I think this is the last thing we're going to do, is L'Hopital's rule. Everybody loves L'Hopital's rule, and that's fine. But L'Hopital's rule can lead you astray. Perhaps we'll see a couple of those examples in the next half hour. You do have to be careful with it. So the idea behind L'Hopital's rule is, suppose that you are trying to calculate the limit of something that looks like a function divided by a function. Okay, so you'd like to calculate this. And it just so turns out that the top appears to be going to 0, and the bottom also appears to be going to 0. L'Hopital says that if this thing exists, then these two numbers have to be the same. So what that means is the thing you were looking at is actually equal to this. So what do I mean by I can run into problems? If you do, say you take the derivative of the top function, derivative of the bottom function, and then you take the limit as x goes to a of that thing, and this doesn't exist, like it doesn't converge, or this limit doesn't exist, then L'Hopital's rule does not tell you that your original thing doesn't exist. L'Hopital's rule tells you nothing. L'Hopital's rule only works if the thing that you're calculating on the right-hand side, this thing, actually exists or is infinity. If that happens, then yes, L'Hopital's rule says that that's cool. That's the answer to your original problem. Okay, so you have to be very, very careful with L'Hopital's rule. We have two versions, believe it or not. We only have two versions. The first version is when the top is going to 0 and the bottom is going to 0. This is called indeterminate form 0 over 0. And as I've told my class, you should never write equals 0 over 0. This is very bad because nothing equals 0 over 0. You might want to put it in quotation marks because that's, okay, I get it. Or you might want to say it's indeterminate 0 over 0. But nothing equals 0 over 0. In theory, that's bad form. So you want to say stuff like it's indeterminate 0, 0. The top is going to 0 and the bottom is going to 0. Therefore, you use L'Hopital's, or however you want to write it. But try not to say equals 0 over 0. So the other version that we have is indeterminate of form infinity over infinity. So we can use L'Hopital's rule in another situation where the top is going to infinity and the bottom is going to infinity. Plus or minus doesn't really matter. As long as they're going to infinity, the top and the bottom, then we can use L'Hopital's rule that says, if you want to know this, it's exactly equal to this, provided this is a thing, provided this exists. If this does not exist, you do the calculation, it doesn't exist, then you have to abandon L'Hopital altogether. L'Hopital's rule does not help you if this doesn't exist. There are other indeterminate forms, but all of the indeterminate forms that you know and love, to use L'Hopital's rule, what you need to do is you need to convert it back into one of these two forms. So some of the indeterminate forms you'll get are 0 times infinity. That's if one of your functions is going to 0, the other function is going to infinity, and you multiply them. You can have indeterminate form infinity minus infinity. As my class knows, infinity minus infinity is not 0. You'd be surprised how many people think it is. Infinity minus infinity is not 0. It's actually indeterminate, so you need to use L'Hopital on it. Other indeterminate forms are indeterminate powers. 0 to the power of 0 is indeterminate. Infinity to the power of 0 is indeterminate. And 1 to the power of infinity is also indeterminate. So in these cases, you want to use L'Hopital's rule as well. But at the end of the day, to use L'Hopital's rule, there's only 2 different versions, and that is these two. Either 0 over 0 or infinity over infinity. So somehow in all of these other versions, you have to turn it back into a 0 over 0 or an infinity over infinity. Okay, so let's try some of them. Let's see what we can do here. All right, so calculate the limit as t goes to 0 of 8 to the power of t minus 5 to the power of t. So this the top is going 8 to the power of 0 is 1 minus 5 to the power of 0 is 1 divided by t. T is going to 0, so this is indeterminate form 0 over 0. Okay, the top is going to 0, the bottom is going to 0, so we want to use L'Hopital. We say the limit as t goes to 0 of 8 to the power of t minus 5 to the power of t over t is equal to, and you might want to put like an LH here or something to let the whoever's looking at this know that you're using L'Hopital's rule, that you didn't just invent something. That is equal to, according to L'Hopital's rule, the limit as t goes to infinity, or sorry, t goes to 0, of the derivative of the top, and the derivative of the top, if we remember our derivatives, is 8 to the power of t ln 8 minus 5 to the power of t ln 5 divided by 1, divided by the derivative of the bottom. So you take the derivative of the top, divided by the derivative of the bottom. So this ends up being the limit as t goes to 0 of 8 to the power of 0 is 1. This is ln 8 minus ln 5. Sorry. It's equal to the limit 8 to the power of t ln 8 minus 5 to the power of t ln 5. And certainly now we can just plug in t equals 0. That's not a problem. And what we get is ln 8 minus ln 5. Or if you want to be really concise about it, ln 8 divided by 5. Ln 8 fifths. Okay, so that would be an example of 0 over 0 L'Hopital's rule. Let's see some other ones. All right, the limit as x goes to 0 of this function. So limit as x goes to 0 of e to the x minus 1 minus x. So as x goes to the 0, e to the x goes to 1. X goes to 0, so this becomes 1 minus 1. The bottom is x squared. That also goes to 0, so this looks like indeterminate form 0 over 0. Okay, so let's actually calculate this. Limit as x goes to 0 of e to the power of x minus 1 minus x over x squared by is equal to by L'Hopital's rule. Take the derivative of the top. Limit as x goes to 0, the derivative of the top is e to the x minus 1 over to the derivative of the bottom, which is 2x. This is also indeterminate 0 over 0. Right, because as x goes to 0, this goes to 1. 1 minus 1 is 0. As x goes to 0, the bottom is also going to 0, so we're going to use L'Hopital's rule again. As x goes to 0, the derivative of the top is just e to the x over the derivative of the bottom is 2. And now we can actually just sub in x equals 0 into this, and we get 1 half. Okay, so those are 2 different L'Hopital rules questions. Let's keep going, see what else we can find. The limit as x goes to infinity of ln x squared over x. So what's happening here? As x goes to infinity, ln x is going to infinity. Infinity squared, if you want to think about it that way. The top is really going to infinity. The bottom is also going to infinity. So this looks like indeterminate form infinity over infinity. Okay, so what we need to do is, we can use L'Hopital's rule in this case, x going to infinity of ln x squared over x. This is what we want. So let's do limit as x goes to infinity of ln x squared. So we're going to use L'Hopital's rule. So this is the derivative of the top, which is limit as x goes to infinity. The derivative of the top is 2 ln x, so the 2 comes down, times the derivative of the inside, which is 1 over x, divided by the derivative of the bottom, which is just 1. So this now looks like the limit as x goes to infinity of 2 ln x over x. Alright, so if we do that, this looks like it is, as x goes to infinity, this is going to infinity. As x goes to infinity, the bottom is going to infinity, so this is also indeterminate infinity over infinity. So we can use L'Hopital's rule again. This becomes the limit as x goes to infinity of 2 ln x. The derivative of the top is 1 over x. The derivative of the bottom is just 1. So this becomes the limit as x goes to infinity of 2 over x. And we can actually do this limit. This is actually 0. Okay. All right, onwards and upwards. Let's find some more complicated things to do. All right, so this, the limit as x goes to infinity. So this x part, x cubed, as x gets really, really big, the x cubed part is going to infinity. But as x gets really, really big, the e to the negative x squared part, that is going to 0, because as x gets really, really big, e to the negative really, really big number gets closer and closer to 0. So this looks like indeterminate form infinity times 0. That's what this is. So we're going to use L'Hopital's rule for this. The limit as x goes to infinity of x cubed e to the negative x squared. However, before we do this, we need to turn this into one of the versions of L'Hopital's rule we actually have. Because remember, there are only two L'Hopital's rules. It's this one, where you have 0 over 0, or it's this one, where you have infinity over infinity. So we need to turn our example into one of those two methods, or into one of those two situations. So what I'm going to do is I'm going to take one of my pieces of my product and I'm going to move it down to the bottom. And I'm going to actually, it doesn't matter in theory which one you use. One might be easier than the other. So if I move the x cubed down to the bottom, it would be x to the power of negative 3 on the bottom. And every time I do a derivative, it's just going to go x to the negative 4, x to the negative 5, x to the negative 6. So it's never really going to get simpler. So I'm going to leave that at the top. And I'm going to move the e to the negative x squared down. So this is exactly, I haven't used L'Hopital's rule here. This is exactly the same as this question. This is indeterminate. As x goes to infinity, this goes to infinity. As x goes to infinity, the bottom goes to infinity. So this is indeterminate infinity over infinity. And now we're in business. Now we can actually go ahead and use L'Hopital's rule. So let's do that. By L'Hopital's rule, this is equal to, let's try that again. By L'Hopital's rule, this is equal to the derivative of the top. Limit as x goes to infinity, derivative of the top, 3x squared, divided by the derivative of the bottom, which is 2x e to the x squared. Okay, so 1x can cancel, this 1x on the bottom can cancel with 1x up there. And so if I simplify that, I get limit as x goes to infinity of 3x over e to the x squared. And as x goes to infinity, the top is going to infinity, the bottom is going to infinity, so this again is indeterminate infinity over infinity. Okay, so I'm going to use L'Hopital's rule again. Limit as x goes to infinity, the derivative of the top is 3, the derivative of the bottom is 2x e to the x squared. Okay, now this is actually something we can take the limit of. As x goes to infinity, 2x is going to infinity, e to the x squared is going to infinity really, really fast. So you have some number divided by a really, really large number. It's getting bigger and bigger and bigger on the bottom. This limit is 0. Because the bottom is going to infinity, the top is just staying a number. So this number goes to 0. Okay, so now we have a situation where we have a limit as x goes to 0 of cosecant minus cotan x. So as x goes to 0, remember that cosecant is 1 over sine. So as x goes to 0, this thing is going to infinity. As x goes to 0, cotan is cos over sine. So cotan is also going to infinity as x goes to 0. So this is indeterminate form. So this is indeterminate form infinity minus infinity. Okay, so this isn't one of the L'Hopital's rule methods that we have, but what we can do is we can convert this into a 0 over 0 or infinity over infinity. So to do that, what we're going to do is, one of the things that you want to try to do is find some sort of common denominator. You need a fraction out of this somehow. So I'm going to look at this and think that, well, cosecant x is 1 over sine x. So minus cotan x is equal to the limit as x goes to 0 of cosecant x is 1 over sine x. Cotan x is minus 1 over, or sorry, is equal to cos x over sine x. So now I can actually look at this and maybe I can combine everything under a common denominator, which I can. So this is now the limit as x goes to 0 of 1 minus cos x over sine x. So a lot of times finding the common denominator between two things will provide you with something that you can twist into L'Hopital's rule. Another situation which we've seen before is sometimes if you multiply by the conjugate. So if you have some square roots lying around, if you multiply by the conjugates, you can actually get things into form for L'Hopital's rule. But here we just use the common denominator, and this seemed to work out fine for us. As x goes to 0, cos x goes to 1, so this ends up going to 0 on the top. Sine x obviously goes to 0 as x goes to 0, so this is indeterminate 0 over 0. Okay, so we're going to use L'Hopital's. And that is equal to, let's take the derivative of the top. Limit as x goes to 0, the derivative of the top is going to be 0. The negative cos x is going to become sine x. And the derivative of the bottom is going to be cos x. And now as x goes to 0, sine x goes to 0, cos x goes to 1. So this just goes to 0 divided by 1, which is 0. All right, let's keep working. Now we get into some of the more interesting, or the most difficult and interesting L'Hopital's rule questions. These are the ones that involve powers. So let's take a look at this. As x goes to 0, this goes to 0, so you have a 1. The base seems to be going to 1, and the power seems to be going to 1 over 0, which is going to infinity. So this seems to be indeterminate of form 1 to the power of infinity. So we can at least hope to use L'Hopital's rule. So this is indeterminate form 1 to the power of infinity. So let's take a look at this. Now, L'Hopital's rule, to twist this into L'Hopital's rule, what we're going to do instead is we're going to say, we're going to, instead of take this limit, we're going to take the limit of the logarithm of this. So we're going to take the logarithm of this. So instead of doing the question that they're asking us to do, we're going to do kind of a side question instead. We're going to do the limit of the logarithm of the thing that they're actually asking us to do. 1 to the power of 2x. So I'll write it this way. 1 minus 2x to the power of 1 over x. This is the question we're going to do instead. Now, typically this isn't a really good idea on an exam. When someone asks you to do a question, you just decide to run off and do your own question on the side because you don't like their question. But in this situation, it's actually going to help us. And let me show you how. So the limit as x goes to 0 of this, because we now have a ln, this 1 over x can come down. And this is why we wanted to take the logarithm of both sides to draw, why we wanted to look at the logarithm of this, to draw the 1 over x down. So this becomes 1 over x times ln 1 minus 2x. Okay, so this becomes equal to the limit as x goes to 0 of the logarithm of 1 minus 2x divided by x. Now let's just see what happens. As x goes to 0, 2x goes to 0, so this inside goes to 1. The logarithm of 1 is 0, so the top is certainly going to 0, and as x goes to 0, the bottom is going to 0 as well. So this is indeterminate 0 over 0. This means that hopefully we can use L'Hopital's rule, so we're going to use L'Hopital, take the derivative of the top and the derivative of the bottom. Limit as x goes to 0 to the derivative of the top is 1 over 1 minus 2x, that's the derivative of ln, times the derivative of the inside. The derivative of the inside is negative 2. And then divided by the derivative of the bottom, which is just 1. Okay, so let's just see what this is. Limit as x goes to 0 of, this ends up being negative 2 over 1 minus 2x. So now we're in a situation where we can plug in 0. We can just plug in x equals 0 into this, and that's no problem. Plugging in x equals 0 to this gives us negative 2 times 1 minus, or divided by 1 minus 0. So this limit is negative 2. Okay, so that's fine. That is an answer to a problem. It is not the answer to the problem. However, how do we get back the actual solution to what they want? The way to do it, the question that they're asking, this, what is this limit, is to take the value that you just calculated by doing this different kind of side project and putting it in the exponent of e. That is the answer they're looking for. And the reason that this works is due to the fact that if you were around for the continuity discussion earlier on this morning, what ends up happening is because the logarithm is continuous at the point e to the negative 2, what you can actually do is you can pull the limit inside e to the I'll show you how it works in a second. Actually, why don't I do it right here? So the reason this works is the thing that they're looking for is this. Obviously, you could rewrite this if you were really inclined as the limit. So I'm just going to put here y. The limit as x goes to 0. If you were really inclined to and wanted to write it this way, you could write it as this function that they're giving you, e to the ln of 1 minus 2x to the power of 1 over x. Let me try to write that in a better way. Right, because e to the ln of this just comes down, and you're left with that. So that's actually what they're asking you to do in a kind of convoluted kind of way. And because you know that you ran off and you've calculated this limit, and this limit is negative 2, and you know that the exponential function is continuous at negative 2, that allows you, because of properties of continuity and composition of function, that allows you to pull this limit inside the exponential because you know the exponential is continuous at negative 2. So this actually can come inside, and you do the limit as x goes to 0 of ln 1 minus 2x to the power of 1 over x, which is precisely what we just calculated. This thing is negative 2. So that's why it works, because once you calculate this negative 2, you know that the exponential is continuous at negative 2, so you're allowed to just pull the limit as x goes to 0 through and into the exponential and put it up here in the exponent, and then this is the actual calculation you just did. Right? We just did this calculation, it's negative 2, and so we can just conclude with that. Okay, so that's why it works. Of course, if you want to write that all out, that's impressive, but usually you can just skip down to the end and just say that's e to the negative 2. So let's try another one. All right. The limit as x goes to infinity of x 1 over x, this is indeterminate. As x goes to infinity, this is infinity, and the power is going to infinity. The power is going to 0, so this is indeterminate. Infinity to the power of 0. So this is one of our infinity to the power of 0 is one of our indeterminate forms. So we know that this is indeterminate infinity to the power of 0, so we're going to use L'Hopital's. But before we get started, instead we're going to take the limit as x goes to infinity of the logarithm of the thing that they're interested in. X to the 1 over x, which is equal to the limit as x goes to infinity of 1 over x ln x. Okay, so that is 1 over x ln x, the limit as x goes to infinity of that. Limit as x goes to infinity of ln x over x. This is indeterminate infinity over infinity. Top is going to infinity, bottom is going to infinity, so I'm going to use L'Hopital. To use L'Hopital on this, take the derivative of the top and the derivative of the bottom. This is the limit as x goes to infinity of ln x. The derivative of ln x is 1 over x. The derivative of x is just 1. So this is the limit as x goes to infinity of 1 over x, which is equal to 0. So that's the limit as x goes to infinity of the log of what they wanted. So at the end of the day, what do they actually want? The limit as x goes to infinity of x 1 over x is equal to e to the 0, because you just calculated 0, so put it in the e, which is just 1. Okay, got a couple more to do, and then we'll call it a break. Calculate this. So what is this limit? So limit as x goes to 0 of x to the power of x. This is indeterminate of form 0 to the power of 0. So we've seen this is of this term, 0 to the power of 0. So this is indeterminate 0 to the power of 0. So let's try to use L'Hopital. But again, because it's a power, it's one of these power indeterminate powers, what we're going to do is we're going to calculate instead the limit as x goes to 0 from the right of the logarithm of what they want us to calculate. So that becomes the limit as x goes to 0 from the right of x ln x. And this as x goes to 0 from the right, this goes to 0, and ln x as x goes to 0 goes to negative infinity. So this is indeterminate form 0 times infinity. So we've seen this before. So let's just try to figure out how we're going to do this. So the way we did indeterminate products before was we took one of these pieces and put it on the bottom of a fraction. So which one of these is actually going to be easier to deal with? If we put ln x on the bottom, that might work okay. But it would be 1 over ln x, and I feel like that's going to get more and more complicated as things progress. So what I'm going to do is instead I'm going to stick the x on the bottom and see what happens here. Limit as x goes to 0 from the right of ln x over x to the power of negative 1. So that's 1 over x. As x goes to 0 from the right, this goes to infinity or negative infinity. This also goes to infinity. So this is indeterminate form infinity over infinity. So now we're in good shape to use L'Hopital's rule. So by L'Hopital, what I get is the limit as x goes to infinity from, or x goes to 0 from the right is 1 over x, because that's the derivative of ln x, divided by negative x to the negative 2. If I rearrange that, I get limit as x goes to 0 from the right of the negative stays out front, and the x squared comes up, and I have x squared over x, which is equal to the limit as x goes to 0 from the right of negative x. And as x goes to 0 of this obviously equals 0. So at the end of the day, we have a situation where the limit as x goes to 0 from the right of this is 0. So the question that they're actually interested in, the limit as x goes to 0 from the right of x to the power of x is equal to e to the power of the thing that we just calculated, e to the power of 0, which is 1. Okay, so let's see what this example is all about. So as x goes to pi over 2 from the left. What happens as, so if we rewrite this, this is the limit as x goes to pi over 2 from the left of 1 over cos, that's what secant is, divided by sine x over cos x. Okay. As x goes to pi over 2, secant x, which is 1 over cos, goes to infinity. And as x goes to pi over 2, sine x over cos x also goes to infinity. This is of the form infinity over infinity. Okay. So let's use L'Hopital's on this. This is L'Hopital's. We're going to use L'Hopital's on this. So it is the limit as x goes to pi over 2 from the left of the derivative of secant x is secant x tan x divided by the derivative of tan x secant squared x. And so what we get is we're going to get the secant x canceling with this, secant x canceling with that secant x, and so we're left with the limit as x goes to pi over 2 from the left of tan x over secant x. Okay, as x goes to pi over 2, tan x goes to infinity, and secant x also goes to infinity, and so this is indeterminate form, infinity over infinity. So let's use L'Hopital again. This is the limit as x goes to pi over 2. The derivative of tan x is secant squared x. The derivative of secant x is secant x tan x. And this secant x cancel with this secant x, and I'm left with the limit as x goes to pi over 2 from the left of secant x over tan x, which is exactly what I started with. So we're kind of in a tough spot right now. L'Hopital's rule, I guess I could take L'Hopital's rule again, but again that'll just give me tan x over secant x. So we're kind of in a tough situation where L'Hopital's rule isn't really helping us out all that much. So what could we do instead? One thing that we could try is we could go back and we could scratch all this L'Hopital's rule stuff out, and instead we could rewrite this as, or let's see if this works, the limit as x goes to pi, oops, from the left of 1 over cos x times this is 1 sine x over cos x, so this is cos x over sine x. I think I got that right. Is that correct? So the cos x's cancel. What I'm left with is the limit as x goes to pi over 2 from the left of 1 over sine x, which is equal to sine of pi over 2 is equal to 1. So the limit as x goes to pi over 2 from the left is 1 over 1, which is equal to 1. So this is a situation that if you blindly just trust L'Hopital to solve all your life's problems, you actually might get into a situation where L'Hopital actually doesn't really help you out that much. So you want to make sure that you remember these other limit-taking rules, like factoring, cancellation, rationalization, and those special formulas that I showed you before earlier this morning, where you had the limit of sine x over x as x goes to 0 is equal to 1, and those special trigonometric limits, because they might come in handy as well. So I guess I wanted to end this segment on L'Hopital's rule by just saying that yes, L'Hopital's rule is great. It can help out in a lot of situations, but it can't help out for all of them, and in fact sometimes it can lead you astray. Like for example this question that we're doing here. In fact, we were able to just do this after 2 L'Hopital's rules. We kind of came to the conclusion that L'Hopital's rule is not going to work. There are situations where, especially when you have tans and secants and cosines and sines, where you might keep doing L'Hopital's rule and you might keep getting a different answer. So it doesn't look like, it looks like you're actually going somewhere, when at the end of the day you're just making things worse and worse and worse. So I just wanted to give you a warning. While yes, L'Hopital's rule is quite handy, it doesn't solve all your problems, and you can't just use it all the time blindly. So that's it for this section. I'll be doing 3 more hours from 6 until 9, and we'll be talking about integration. So just integrals, substitution method, that kind of stuff. And so hopefully you guys can join me for that. And if so, I'll see you then.